Hello, sir.
Yes,
Hello, sir.
please.
Can you hear me?
Yes, go ahead.
I'm I'm Jawahar Prakash, PhD, IIT Madras,
Mm-hmm.
Patna. I'm working on foreign film measurement, foreign film studies, curricular foreign film studies using holography. Trying to use holography.
I think you're a little bit breaking up, right? So, okay, you can put it in the chat box or something.
Okay.
Oh, adaptive optics. Okay, all right. Thank you. Uh-huh. Okay, okay.
Next one.
Is there someone else? Okay.
Yeah. Yeah, not there.
Oh, okay. So this is one, and then no, this is the IIT Kharagpur. Okay, got it. And then Yaspal Singh. Okay. All right, later on when he comes. Okay, thank you very much. Okay, so then maybe I'll continue with these Kukhtarev equations, and we'll take the rest of the time to do this, and then Professor Nischal is going to come and talk about interferometry. And after he talks about interferometry, I'll continue with interferometry because he's done a lot of work on interferometry as well. So, oh, I need to put on the microphone. So before the break, we talked about the Kukhtarev equations, and I said that these equations are not easy to solve at first. Okay, so these equations, of course, are not easy to solve. Sometimes you can solve them in the steady state. In the steady state, sometimes these equations can be decoupled, and when they're decoupled, you can find out the steady state. Oh, sorry, should go to this mode. Okay. So in the steady state, you can actually solve these equations after some simplification. Then you can show that the space charge field is approximately proportional to the gradient of the intensity. But if you want to solve these equations in time and space, then of course it's very hard to do. So people usually do what's called a perturbative approach. So in the perturbative approach, people usually take, again, those equations over there, but then they assume a form of intensity distribution function. The intensity is taken as the interference pattern between two waves. One of the waves is called the pump and one is called the signal. And then you take this and then you put it in the Kukhtarev equations where the intensity is. And also assume that the modulation depth is small. Otherwise, you cannot linearize these equations. So it's a long process. So you take this, put it in the equations, assume that this modulation index is small, then expand all of these dependent variables into a steady state term plus a first order perturbation. That's typically how it is done. And when everything is said and done, then you can find, of course, these approximate expressions for these guys, the ionized donor concentration, electron concentration, the current, and the space charge field. Those are the four variables. But then that's not the end of the story. Then you need to again go back and then try to put those into Maxwell's equations. Because in the Maxwell's equations, now what you need to do is put them in the constitutive relations. Because in the constitutive relations, so you have the epsilon. Epsilon is the permittivity. And permittivity is modulated because, the change of refractive index causes the change in the permittivity. So those relations are here. Okay, I mean, these are standard relations for epsilon. And then once you know the permittivity change, then you can find out the new optical field equation. So you see, it's a very complicated process. And if you look at Pochi-Ye's book as an example on photorefractive optics, you'll see These derivations are done in detail in, I would say, like chapter 3, somewhere around there. But it takes quite an amount of time to do it. But when everything is said and done, you can find, as you can see, a kind of simplified, of course, simplified equation for the evolution of the space charge field. Okay, the evolution of the space charge field. So the evolution of the space charge field, of course, what is not written here is that this is the evolution of the perturbation in the space charge, because otherwise you cannot solve the equation. So really, when these equations started, it was written as ESC with a superscript 1 on the top. What does the 1 mean? The first order perturbation. But now it has been deleted. Okay? So this equation, as you can see, of course, is a simpler equation, simpler rate equation. So this rate equation can be solved. Okay, this rate equation can be solved because, it's a very simple kind of equation. And all of these terms here have definitions. Definitions of A, B, and C are kind of all written over here. This M is this modulation depth, as I said, of the intensity grating. A depends on some of these parameters. Some of them is called the diffusion field. Some of them is another applied field, if there is one. Another one is the EM, which is defined over here. Then there are other constants B and C and so on. See, this constant C also has the EPV in it, which is the photovoltaic electric field. Okay, so when these equations, are solved, okay, when these equations are solved, you can find the space charge field. Once you find the space charge field, then you find the change of refractive index. When you find the change of refractive index, then you can put it into the optical field equations. And in the optical field equations now, you can derive, as you can see, the space rate of change of the pump intensity, the signal intensity, and the phase difference between the pump and the signal. So it's a very complicated process, and I don't want to, bore you with that. But let's first look at this one, this equation here. This equation is the rate of change of the space charge field. And if you only just consider steady state, okay, so then you see this ESC is just a kind of simpler expression, which can be expressed in terms of these constants, B and C. And if you put those in, this is how it looks like. Okay, so in this expression, you see the space charge field, of course, depends upon the modulation depth. Another thing also you notice here, it depends, of course, on the externally applied electric field, if there happens to be one, depends upon the diffusion component and the photovoltaic component, right? So these are the different terms. So you see the presence of I, which is really J or minus J, this because this is taken from Pochier's book. The presence of this tells you that this space charge field is out of phase with the intensity modulation by 90 degrees for diffusion dominated photorefractive effect. Whereas if you have photovoltaic effect as the dominant contributor to the space charge field, then the electrostatic field is in phase with the intensity modulation. So that's really what this equation states. And these different things are actually defined, as you can see here. Space charge field, is defined as this entire expression can be written something like this. If you take, say, the E0 to be 0 and EPV to be 0, then you are only depending on the diffusion field, right? And sometimes people also plot this gamma. Now, what is this gamma? Gamma is called the gain coefficient. Okay, and this gamma is defined as you can see, proportional to the imaginary part of the space charge field. Okay? Imaginary part of the space charge field. So this gamma gives you the gain coefficient, which tells you the amount of energy exchange that can happen between the pump and the probe. Okay, more the gamma, the more energy exchange you can have between the pump and the probe. And you see, there is another important thing, the dependence of gamma on, as you can see, the grating spacing. Okay, So for any photorefractive material, there is an optimum value for the grating spacing that will give you the highest value for the gain coefficient. So typically, in materials like barium titanate and so on, this angle over here, okay, which is also going to define this capital gamma, is kind of the order of about 20 degrees or so in here. All right, but it's not that you are not going to get gain in other angles. You are also going to get gain in other angles, just that the amount of gain will be less. But this is actually an easy experiment to do also. If you are doing an experiment, if you have a photorefractive crystal like barium titanate, just put in two beams and you can actually see, the light being transferred from one beam to the other. It's an easy experiment to do. But however, if you wanted to plot this curve experimentally, it's not an easy thing to do, just because, you know, um, going to large gamma and very small gamma is not an easy job because you really have to adjust the beams. And this is a plot of capital gamma as a function of lambda, where this lambda is inside the material. So you have to translate that to outside the material and then accordingly adjust the beam size. So that takes a lot of effort. All right. Some of the other things I would like to plot here, this difference between thin and thick grating. No matter how much you try, no grating is absolutely, the perfectly thick grating or the perfectly thin grating. So when you are doing actually an experiment, like the one I showed you there before, sometimes and very often you'll see some higher orders coming up. And whether you get an appreciable amount of higher order or small amount of higher order, as you know, depends upon the Q factor of the grating. And Q factor of the grating, as you all know from any grating theory book, is defined as, this 2 pi times L, which L is the thickness of the grating, times lambda divided by the grating spacing squared, and N is like the refractive index inside the medium. So if the Q is larger, typically if the Q is larger than, I say if the Q is smaller than 1, okay, then you have the Raman-Nath diffraction region. And if Q is more than 10 or so, then it's more like the Bragg region. This diagram is not exactly drawn, um, you know, correctly in the sense that, if you want to have ideal Bragg diffraction, you have to come in at the Bragg angle, and then you get, the undiffracted order and the diffracted order. But if the Q is just greater than 1, you can still come in, at normal incidence. You can get, some amount of light diffracted in the plus and minus 1 orders. I mean, not that it is not going to happen, it's still going to happen. But for maximum diffraction, into say the plus 1 order, you could come in exactly at the Bragg angle, you have maximum diffraction to be possible. This is kind of just a plot of Q, and then as a function of the capital lambda, it's a 1 over lambda square curve, essentially. That's pretty much it. Some of the numbers, that you want to remember over here, values of this Na, which is like an acceptor concentration, typically 10 to the power of 15 per centimeter cubed. This Na is kind of the doping kind of level that you would put inside the material. Typical doping, say for instance in lithium niobate, would be an iron, okay, like an iron 3 plus, for instance. If you have an iron 3 plus, then you have iron 3 plus that actually, or iron 2 plus, I should say, iron 2 plus, and then iron 2 plus gives out electrons and becomes iron 3 plus. But in that case, it's not Na, it's Nd. But if you had acceptors, then typical numbers for biasing or, doping the material is of this order, 10 to the power of 15 per centimeter cube. Right, yeah. You can sometimes dope liquid crystal as well. Liquid crystal has been shown to have very weak photorefractive properties. And, one of the first works that was done on that is by a guy called I.C. Koo at Penn State. He's a well-known person in liquid crystals. But liquid crystals, the photorefractive effect really happens that any appreciable gain happens for very small angles. Typical angles is like 1 degree inside the material. So yes, it is photorefractive, but then I have never seen too much of a practical application of liquid crystals as photorefractive elements. I mean, we tried to do the experiment. Putting in 1 degree inside the liquid crystal is, first of all, not an easy thing to do. No, as I said, liquid crystal photorefractive, you take the liquid crystal itself. There's nothing extraordinary to that. Make a liquid crystal and just dope it with some acceptors. That's it. There's nothing extraordinary. It's a nematic liquid crystal. And I forget what type of material you have to start with because there are different kinds of nematic liquid crystals. So whether it is 5CB or something else, I don't know. I can look that up. Or it's there in that paper by IC Ku, for instance. But if you want to make it photorefractive, the only thing you have to do is just dope it with some acceptors. So these polymers are those the PMMA kind of polymers. They are kind of a mix of four, I think, different materials. Like there's a PVK and something else. I forgot their exact composition. Yeah. Say that again. Maximum number of lines. Oh, spatial frequency. Oh, what is the maximum spatial frequency you can store, you said, in the photoreceptor crystal? Well, actually, that's a good question. That kind of comes from that curve. Depends on the material. I mean, I'll show you some pictures later on. So, where was that curve here? Yeah, so here, typical, maximum spatial frequency would be, somewhere in this range, which I would say spatial frequency wise, it will be like 10 to the power of, if you're doing like green light, the value of K0 is about 10 to the power of 7 radians per, 10 to the power of 7 radians per meter. So I would say 1/10 of that. So 1/10 means 10 to the power of 6 radians per meter. That's the maximum value of K that you can. Change of refractive index is typically of the order, in lithium niobate, I know it's of the order of 10 to the 4 to 10 to the minus 4 to 10 to the minus 5. It depends upon the intensity of light that falls on the material. So approximate formula in, for instance, in lithium niobate, the delta N is equal to or proportional to approximately I, okay, I is the intensity pattern, divided by I plus ID. And ID is what's called the dark current. I sub D is referred to as a dark current. Dark current is the current because of noise inside the material. Well, lithium niobate, typically green is good. Green. No, red is not good because it doesn't excite the electrons to the conduction band. But blue is fine. I'm sorry, say that again. Speckle noise, yeah. Well, that would be true because the wavelength becoming smaller means you'll have more scattering from the. Yeah. We have not used blue. We have only used green. The greens we have used are like 514, and then there is another line of the argon laser at 532. So those are the two lines we usually use. But the other thing we do with lithium niobate also, as I said, these reflection gratings, we store them using green light, but then we sometimes read them out using red light. Yeah, because it is not going to destroy the grating, okay, for some time. Okay, with this? These are some other more advanced stuff, I would say, over here. We were trying to actually see or measure the photovoltaic effect or the contribution of the photovoltaic effect in lithium niobate. So what we did here is we did what is called a Z-scan experiment. Have you ever heard of Z-scan? Okay, so it's a very easy thing. So Z-scan is a way of measuring the nonlinearity in a material. Okay, so that's a one-line definition. Okay, so how is it done? Well, very easy. If you have a nonlinear sample, okay, and let's suppose the nonlinear sample responds by a change of refractive index that is proportional to the intensity. All right, so that's typical for, like chi3 materials. Chi3 meaning, cubically nonlinear materials. But material doesn't always need to be chi3. As long as the change of refractive index is proportional to the intensity, it is going to work. And lithium niobate is such a material. So this particular work was done to characterize different lithium niobate samples. So a lot of lithium niobate crystals were bought from many different companies with different dopants, and our job was to find out, what is different about each one of them. So I decided to do this Z-scan, as it is called. Now, typical Z-scan was introduced sometime in like 1980 by a gentleman called Eric Van Stryland at University of Central Florida. Okay, so it's named after him. So Van Stryland was the main person who discovered this Z-scan. The principle is very simple. So what is done is you just take a laser beam, you focus it with a lens, and put whatever sample you want to measure the nonlinearity of around the back focal plane of this external lens. All right? So the principle is easy. So if you have a lens focusing light into this nonlinear sample, the light will be more intense. If the light is more intense, then of course this material change of refractive index will be larger. Now, if the beam is Gaussian beam, that means you have the most change of refractive index in the middle, where the intensity is the most, and less on the sides, right? So the induced change of refractive index approximately follows the same profile as the Gaussian beam, right? So therefore, the focal length of that induced lens will depend on, how tightly the light is focused and on how nonlinear the material is. Does that make sense? Very simple. So if you move this sample, now I have drawn a thick sample because we extended it to thick sample, but Van Stralen originally did for a thin sample. So let's assume this sample is thin. Thin means, this beam is not changing its shape as it is going through the material. So in other words, the material is just looking like a thin phase object. So then, depending on the width of the beam, okay, the strength of the induced lens will be different. So if you have this sample before the focal plane of the lens, right, then you have a certain, change of refractive index, therefore a certain induced focal length. If you move it through the middle and then to the other side, then you have different different induced focal length. Does that make sense? So as you scan the sample around the z direction or the z direction and look at the far field, okay, look at the far field, simplest picture is just think of a combination of two lenses, okay, and just ray theory, okay. So this lens is trying to, tighten the beam, and if the second lens, say, is a positive lens, all right, if that positive lens is before the front focus of or back focus of this lens, it's going to further, you know, uh, uh, focus the beam down, and if it further focuses the beam, after the focus is going to diverge at a larger angle. So therefore, on axis, the power will be less. Right? Very simple. And if you do it the other way, okay, if you put the sample past okay, the back focal plane of this lens, again, it's going to be a positive lens, but then by that time, the beam is already diverging, and then it diverges less. And therefore, the power here will be higher than what you had before the lens. So then, if you plot the on-axis change of intensity or power as you scan the nonlinear sample, to the left, the width will be larger, therefore the intensity will be less, and past the back focal plane of the lens, the width will be less, therefore the intensity will be more. So if you plot the slope of change of intensity with the scan distance, it's going to be positive. The positive signifies a positive lens, first of all, and from the slope you can find out the value of the nonlinearity. Okay, so this is what is called the closed aperture Z-scan. And then you have something else that's called the open aperture Z-scan. Again, very simple. That means how much power is, falling all total on the, screen. And that depends upon the absorption in the material. Sometimes you have nonlinear absorption in the material. So that's this principle of Z-scan. It's very commonly used technique to characterize nonlinear materials. Actually, as it turns out, you can also characterize linear materials like a lens. If you have a regular lens, okay, you can also characterize it exactly the same way by moving the test lens about the back focal plane of a lens that you know the focal length of. And so you can extend this for characterizing linear lenses as well. And in fact, we did that. And so we have a patent on that as well, how to use this for linear lenses. But okay, besides that, so here we wanted to find out how good of a volume grating you can store in this material. Therefore, we wanted to know how good of a delta N there will be. Now, lithium niobate or any crystal electro-optic material is anisotropic, right? Remember that? Anisotropic. So then this lithium niobate has what is called a C-axis. Okay, it has a C-axis. So light polarized along the C-axis will see the maximum change of the refractive index. All right. So in this case, the light was sent in horizontally polarized and along the C-axis of this lithium niobate sample. Are you okay so far with it? So now what happens as a result of that? So now here, the width of the beam along the X direction, of course, will change, right? Because it's going through a further induced lens. But the width in the Y direction, it'll change also, okay? But it's not going to be affected because there is no change of the refractive index along that direction. So therefore, finally you see an elliptical shaped beam coming out. Does that make sense? Why should be elliptically shaped beam? The elliptical shape comes from the fact that the maximum change in the refractive index is happening along the, x-axis, which is the c-axis. So therefore, this is an easy experiment to do. So you'll see the beam evolves into an elliptical shape. Okay, this kind of shape, okay, some people have also called it beam fanning in photorefractive materials. Now, beam fanning happens in photorefractive materials because of noise, actually. And beam fanning is particularly a problem sometimes in crystals like barium titanate and so on. Also in crystals like lithium niobate. But the beam fanning that happens from noise meaning scattered light in different directions, and then amplified scattered light because of two beam coupling, okay, I have called that random beam fanning. Okay, as opposed to this one, because here also the beam is fanning, meaning it is becoming, kind of broader in one dimension. This one I call deterministic beam fanning because why? This is not happening because of scattered, noisy components of the light. Are you okay with this? So there are two components to beam fanning. So typically, I would say when first work was done on beam fanning, it was in barium titanate crystal. And that beam fanning was shown by Jack Feinberg at University of Southern California sometime in early 80s, along with Nikolai Kukhtarev and others. So that is really random beam fanning. And this one is more like deterministic beam fanning. So here, so what we all did, only thing we did, we scanned the sample. We found out the ellipticity of this beam in the far field. Okay, and from that ellipticity, then we could find out the change of the refractive index. Does that make sense? And from the change of refractive index, you can find out the effective, nonlinearity coefficient, which depended on these parameters, which are really material parameters. So from there, we could characterize. Really, what we wanted to characterize is this Na over Nd ratio. Okay, the acceptor to donor concentration ratio, which is a very important parameter for these photorefractive materials. So again, good question. So in these materials, remember I said one of the popular dopant materials is iron 2 plus. Okay, so iron 2 plus is the donor. All right. So iron 2 plus is the donor, but what is interesting is when the iron 2 plus ionizes and then it releases an electron, it becomes what? It becomes iron 3 plus. And that iron 3 plus works like a trap and also like an acceptor. Okay. So that iron 2 plus to iron 3 plus ratio is very important here. So here, this Nd corresponded to the iron 2 plus concentration and Na corresponded to the iron 3 plus concentration. But that's not the end of the story. Anytime you start to make a crystal, and that's why I'm saying it's very important, there is already a lot of resident impurities because, when you start making a crystal, first thing you do, a crystal doesn't grow in vacuum. Otherwise, you have to send it in the space shuttle or the space station. You have to start it, some kind of a impurity, then it develops into like the boule, and then you have some kind of a boat or something where you hold the sample. So all of them are sources of impurities. So another very common source of impurity happens to be, I think, nickel. And it depends on where it was grown because this container, okay, the container that you are starting this thing in, or the seed that you are starting, they all affect what the impurities are going to be. So different manufacturers have different seeds that they start with. Say that again.
Is that for the perovskite material heavier?
Yeah. Okay, so understand this more or less here. So that's what we did. As you can see, this was the experiment, that was the results, and then we characterized that, and that's fine. One of the other things you'd like to also know using this lithium niobate, this always happens. So you're trying to use lithium niobate as this volume holographic element. So you want to write some grating inside, right? So you are, so how do you write the grating? Well, so a reflection grating, okay? So you are shining in a beam of light, okay? And then letting it sit for some time. Because, see now, how is the reflection grating written? That's another good question. So this is, of course, transmission, but when you're writing a reflection grating inside this material, you're going to send in light in this direction, right? Yes, sir. And then that light is going to back propagate because of Fresnel reflection. As it back propagates, those two beams are going to start interfering with each other. That interference pattern will create the optical grating, and the optical grating will start to build up the phase grating inside the material. Does that make sense? Okay. Yeah.
Non-linear sample will work as a lens for any type of laser light or only for InCAM?
No, any kind of laser light. Depends on, this material if it responds to that particular laser light. So, in this case, lithium niobate would work as a nonlinear lens if you put in green light.
Like we work as a rhodamine, non-linear sample. So in that case, like some type of neon laser,
Yeah, yeah. Right, it'll work. Rhodamine will work. Yeah, correct. So anyway, so this is how you make the reflection grating inside the lithium niobate crystal. But now another thing that happens is you can never write a uniform modulation depth reflection grating. Why? Because the moment you start writing the grating inside the material, guess what happens? More light is reflected back because it's a grating, right? So more light is reflected back, therefore less light is transmitted through. So where there is less light, there is less grating being written. Does that make sense? So you start writing the grating with green light, yes. The first grating writing starts from this light going in, then being reflected. So you have a standing wave, so to speak, optically standing wave inside the material. That starts to write the grating, like, the delta N starts to build up because it's all a function of time. Okay, it starts to build up. But once it starts to build up, okay, then the light that's coming from this side further gets reflected because there is already a little grating inside. So as this light is reflected, less of the light is going into the bulk of the medium. Therefore, you have less of a grating being made. So the strongest grating is made, nearer to the entry face of the light where you're starting to write the grating. Does that make sense?
That's why at the review.
Yeah. So actually that always happens. So you can do all the theory you want, but finally, when you want to do a practical experiment like we are trying to do, like this image processing as well, we have done the simulation for uniform grating. Will not work. Yes, it works. I mean, up to a certain point, qualitatively is the same. But if you want to do quantitative analysis, you now need to find out how the peak of the grating, like the delta N, changes as a function of depth inside the material. And that's a complicated, work. I mean, some people have done it, actually. And what they have shown is that most of the grating happens within the first about 1/3 or so, 1/3 of the depth of the crystal. Okay, then, the grating strength decays down. So how did they find that? That's also interesting. They wrote the grating, started writing the grating as a function of time. Then what did they do? They actually put in, this is very interesting, they put in an erasing beam from the side. Okay, they put in an erasing beam. You can erase gratings in lithium niobate. They put in an erasing beam from the side to erase part of the grating. And then they looked at the reflected light. So by monitoring how much reflected light came out from where they erased the grating, they were able to figure out the spatial profile of the grating. It's not an easy experiment. And I can give you the reference of that paper as well. So some of the other things that Professor Nistel is going to talk about, correlation. You can do correlation using these volume grating materials, photorefractive materials. This is a case where we did actually, and I'll talk about it, later on. So here, what you do is essentially shine, kind of two beams, like T1, T2, the things that you want to correlate. And this you can see is a front focal plane of a lens. So in the back focal plane, you're really writing the Fourier transforms, right? You're writing the Fourier transforms. And here you're kind of jointly writing the Fourier transforms of T1 and T minus 1. So that is written inside the material, and then you read it out with a reading beam. When you read it out with a reading beam, you can get the correlations, okay, or convolutions, whatever you want to call it, between T1 and T minus 1. So this is a standard way of doing, in this particular case, it's called this joint transform correlator. Remember we were talking about that? Joint transform means I have stored the Fourier transforms of both T1 and T minus 1, and now I'm reading it out with a reading beam. And actually another little thing to talk about here is this grating is kind of semi-thin grating in a sense. So when I'm reading it out like so, I'm really monitoring what are called the non-Bragg orders. Okay. But those are, kind of second order detail. But the main thing is I've written down here the Fourier transforms, the product of the Fourier transforms of both T1 and T minus. That's what I've done. And then I'm reading it out with a plane wave. So when I read out the Fourier transform of, say, T1, call that capital T1 multiplied by capital T minus 1, then on the back focal plane of one lens, I'm going to get the convolution or the correlation, right? Because it's another Fourier transform. So these experiments have been done. Actually, these are some of the results. Actually, one of the other things we also did is we chose a material where you can also do edge enhancement of the object as you are writing the correlation. So the object with edge enhancement is like so, and then you have the joint transform correlator without edge enhancement and with edge enhancement. Edge enhanced correlation is always better. Uh, you'll hear that also from Dr. Nischal. Why? Because, let's suppose you have a square wave, okay? Square wave correlation with a square wave is a triangle, right? But if you edge enhance the square wave, say you take the derivative of the square wave, you get two delta functions. And then correlation of the two delta functions with itself is going to give you very sharp correlation. So that's why edge enhanced correlation is always better. Okay, so organics versus inorganics, I have some slides here. I mean, index modulation can be large. Index modulation can be large, but then at the same time, as I said, there are other practical difficulties, of organic materials. I didn't put in more slides about these organic materials just because I thought, well, we're not going to talk too much about organic. But since some people are interested in organics, if you want, I mean, on this computer, I have some typical compositions. I can let you know. And in fact, shall I escape from here? I have 4 more minutes. Let me just show you. Oh, any questions before I stop here? So this is all I wanted to cover about photorefractives for now. I'll get back to it later on when it comes to like phase shifting and so on.
Photorefractive index and the polymer change. The correlation depending upon the photorefractive
Yeah, unfortunately, I am not a specialist or a chemist. So that's why I don't know, actually. And that is true. There it is. So I don't know. But I can actually go and show you actually a paper. The person I used to, I'm sorry, age enhancement. Right.
So right now some digital technologies are also available, like the intelligence processing technology. There are some algorithms.
Oh yeah, yeah. I mean, a lot of digital.
What is the advantages of this analog?
So good question. I always get back to, this business of fashion. When I was growing up, I went to Catholic school like Don Bosco in Calcutta, and we had to wear uniform. And I came from a strict family. My father would take me to a department store. It was called Kamalai. It's an old department store. It's very good, where there was an old tailor who would tailor my pants. And those pants were those double-pleated black, double-pleated, very loose pants. So when I would go to school, I would be made big fun. It was only after I finished my IISc exam, I mean the senior Cambridge exam, that my father allowed me to go to a store in Calcutta called New York, where I made tailored, the drain pipe pants and bell bottoms. Okay, so time goes on, right? Those baggy pants are back, double pleats are back. Again, they're gone. There are no pleats, so they go inside. So initially, when people started talking about optical computing, Okay, they were very enthused about all this work that optics can do, which is, in the 60s, 70s, and so on. Then people saw, well, computers can do this job much faster. Yes, it's true. And computers do. But guess what? Now, fashion is going back to optics because there are plenty of micro optics. I mean, and in the getting to the size of like meta lenses and so on. So now the technology is steering back to optical processing as much as possible, especially this convolution correlation. And then again, in a few years, something else will happen and it will change. But no, it is getting back actually. Nowadays, you'll see plenty of SBIRs or calls for proposals where they are talking about analog computing because that will save time from the computer. And I will also say my personal opinion is, we are in a sense consuming too much power with the computers. And so we could look for more efficient ways of doing these kinds of computation wherever possible. We are really warming up the earth with all the data mining. Uh, that's why all these, data centers are establishing themselves in, Iceland and other places. And to me, that cannot go on. You have to find more efficient ways of even doing things like ANN and all kinds of other stuff. Okay, so that aside, I just wanted to show you maybe,
Sir,
yeah.
you talk about the erasing of grating on the protective material. So on what factor that erasing time depends upon, like how fast we can.
That's another good question. That depends. In lithium niobate, typically you can erase by raising it above a little bit of Curie temperature and then letting it slowly cool down. So that takes, kind of almost overnight, or at least 2, 3 hours.
Can we decrease that time for that upgradable?
It'll crack. It'll crack. That's the problem. These crystals are very brittle. So that's why you have to do them slowly. Another thing I have found personally, the better way to do is just keep it under a table lamp overnight. That does a good job. Then not the LED table lamp, the old-fashioned incandescent table lamp. That gives out some heat. Oh, many times, many times. Yeah, you can look at it actually under the microscope. You'll see, if you see that it is kind of become, you know, um, cloudy, that means there is grating. When it's gone, it's gone. You can keep going. So here, this is one of the ones that I have personally used. I mean, this is this composition. So you want to. No, so that's why. So lithium niobate can do some jobs. So in some places you want to store the grating. In other places you want to quickly erase the grating and go on. There you use faster materials, like potassium niobate is a very fast material. So the word dynamic depends on who you talk to, right? If you talk to a snail, okay, I mean, lithium niobate is very dynamic. But if you talk to me, potassium niobate is much more dynamic. So this is the kind of composition of the material. And these work, I mean, I tried making them actually. So there's an interesting story. So I learned how to make this in Japan. Okay. Then I came back and I told my student, his name, as I said, Isam Gad. He's an Egyptian guy. Anyway, so I wanted to get these materials, right? Because you need raw materials. Now, as it turns out, all of these you can get except this last one. See, the last one, the first two letters are T and F, T and N. The last letter instead of F, if you had a T, it would be TNT. So this TNF is a cousin of TNT. And you know what TNT is, right? Yeah, it's a dynamite. So it's a very explosive material. So when I wanted to make this, I was in Huntsville. So I called different companies. There was a company in Chicago that said, yes, we have this. And they said, okay, I mean, the price is very small. Okay, I want some milligrams, right? Price is very small, but to transport it, we need a special transport because it's an explosive material. So it'll cost $1,000. Okay, so we said, okay, no, I can rent a car and I can go to Chicago and I can pick it up. So my student and I, okay, we rented a car and then we went. So the name of the student is here. So this guy is some guy. Okay, so and this is something we did with photorefractive polymers, this correlation. So then we drove to Chicago and then we went to this company. This company said, yes, you can take this entire bottle. So I said, no, sir, I wanted, some 5 grams or whatever. He said, no, we want to get rid of it. So that entire bottle had 5 kilograms. So then he said, so I said, okay, fine, we're taking it. Then he said, sir, before you go, and this is in summer, before you go to Walmart and buy a pillow. And he said, why? Because this powder, if it shakes, okay, they can actually catch fire. So, so then we went to Walmart, we bought a pillow. My student drove half the way. I sat on the back seat with the pillow and this bottle. And then we finally came back. And then we made actually, and this paper was done with material that we brought back from Chicago. And so here we actually did the correlation and convolution as the one section. Okay, I hope I have talked enough about photorefractives. If you want to know more, let me know. And I'll just stop here. And after the break, I think Professor Nischal is going to come and talk about interferometry. And if you have any questions, please ask. Yeah. Sure. Okay. I will. All right. Do you find it interesting? Okay. Online guys? All right. I think online guys are watching, but I would love to go online as well. No, I don't want to leave the meeting. Do I want to leave the meeting? Oh, yes, sir. Okay. All right. Oh, he wants me to leave the meeting? Is that what? Yes, sir. Okay. All right. Thank you. So what do we do now? Do we take a break and Dr. Nischal comes, or what does it do? Maybe you can check.
Share me the photo, the polling
Paper?
paper and suggest me how to work. I am already working.
Okay. I have not worked actually in a long time on the polymers. As you saw, the last time I worked with 2000, but I can share what I have. Send me an email, I will send it. Yeah. Okay. Send me an email. Right? Yeah. Sure. Sure.
If any doubt further, I will discuss with you regarding.
You have to place the premium material to the original material.
Yeah. Right.
Who is the just like good?
Further research perspective.
That one I don't know because as I said, I was just following a recipe. I was just following. So I mean, actually, the person I will say who knows about it, I'll find. I'm forgetting his name, but he was at University of Arizona. He has now moved. But one of the things I will talk about here is this digital holographic reconstruction. Okay, so when you make a hologram, right? When you make a hologram, you need to reconstruct, right? So how do you reconstruct? Well, there are those 2 or 3 different ways, but main thing that you have to do is take the hologram, assume that the hologram is illuminated with a plane wave, and then either do forward propagation for the real image or backward propagation for the virtual image, right? So that's the basic thing. How can you do it? Well, I know of only one way to do it, which is use the transfer function for propagation, or of course the diffraction formula, one of the two, right? So that's it. So here in holographic books terminology, the hologram function is usually written as H. And this is the notation that's used in like Schnarrs and Buchner or in many other books. So H is the hologram function. Remember that because this H we have used before for the impulse response for propagation. But this H is now the hologram function. So this is eliminated by the reading beam. Okay. Reading beam technically is taken as to be the conjugate of the reference beam that was writing the hologram, but for most practical purposes is taken to be one, meaning just a plane wave. That's it. Just like when you were actually making the hologram, the understanding was the reference wave was a plane wave, although it is not in most cases, but okay. So in digital holography books, this is the kind of formula that's written. So what does this formula say? This formula says that this gamma, okay, this gamma is the reconstructed object, if you want to call it, or image, okay. This is another issue I have, which is these notations, okay. So these notations, they're written as psi and eta, okay. It's copied from Schnarr's and Jupner's book. Okay, and what it is, okay, you have the hologram function that's illuminated by, in this case, really a plane wave. So this is a plane wave, which is like 1. So this is the complex field immediately after the hologram. And then what do you do? Well, you have to convolve it. In the space domain, you convolve it. I'm sorry? Oh, full screen, sorry. There, how is that? Okay, so you have to convolve it. You have to convolve it with the impulse response for propagation, right? So this is the convolution integral. So this convolution integral can be done in many ways, right? One is, yeah, you can do actual numerical convolution. The other thing you can do, as I prefer to do, I would take the Fourier transform of this hologram function, multiply it with the transfer function for propagation, and then propagate and take the inverse transform. That's what I would do. So some people use what is called the angular spectrum approach. That's what I just mentioned. Some other people use convolution. That means they literally take this and perform numerical convolution. But the most popular thing that people do, you'll find in most digital holography books, is what they call the discrete Fresnel transformation. Okay? I'm particularly, kind of unbiased in a sense. Some of my students do this discrete Fresnel transform. I prefer them to just take the Fourier transform of this, multiply by the transfer function, and take the inverse transform. Okay, but since most people, in digital holography books talk about discrete Fresnel transform, let me say what that is about. So discrete Fresnel, okay, so discrete Fresnel transform, this is just let me write. So this is what the discrete Fresnel transform is. So what is done there? Well, let me go back here. See this equation? This G is this guy, right? G is this guy. And this is the, as you can see, the non-paraxial, the non-paraxial form. But you can also take the paraxial form, whichever one. But you see, essentially it's a convolution, right? Essentially it's a convolution. So going back here, see the same thing is written here. The convolution has been broken up, okay, because remember what you have there? You had this term. You had this x minus psi squared y minus eta squared, right? Then if you would take the square root of this and assume that this d is much larger than this, then you're going to get a binomial expansion. The binomial expansion is only going to have x minus psi squared and y minus eta squared, right? That, if you break it up, will have 3 terms each, x squared, x 2 times x times psi, and psi squared, right? Make sense? So that's what is done here, okay? The same thing has been written, except just in a different form, right? Except in a different form. So the part that does not depend upon the integration, which is the quadratic part in psi and eta, has been taken out of the integral, and rest of the terms have been kept within the integral. You okay so far? All right, so now you just look at this equation, you see it's as if you have this h, and forget about this, it's just taken to be 1 usually. So h and then times this guy, okay, this product is being Fourier transformed, right? Because you see this part here looks like the Fourier transform integral. Does that make sense? It looks like the Fourier transform integral if and only if you think of this part which is 2 pi over lambda d and then times the psi as a spatial frequency, like kx. And same thing here, 2 pi over lambda d times the eta to be ky. So it's exactly like what's called the scaled Fourier transform, right? The scaled Fourier transform. So this guy over here, the way this integral is computed is not by just using standard convolution, but instead using the Fourier transform operator, which is written here. So what you do is you multiply this with this phase curvature term, then you take the Fourier transform, and then you scale the spatial frequencies, namely kx and ky. So many people choose to do this. Okay, so this is called this, discrete Fresnel transform, which in discrete form is written over here. All right. So many people do this. As I said, my preference is not that. My preference is, if you have this, take the h, take its Fourier transform, multiply it with the transfer function for propagation, and take the inverse transform. But whichever, both of them give the, exactly the same result. So that's actually what I wanted to talk to you about over here. And you can go through the details. I'll give you these slides as well. You can go over the details and see. So I wanted to stop there, but then I wanted to actually ask you about how you're doing with the little assignment that I gave you. Did you manage to plot a Gaussian? No? And why would that be? I know, because you didn't switch on the computer. That's one reason. Assuming you switched on the computer, did you get any plotting program or maybe MATLAB or something? Yeah. I think you should probably start with the plotting. So I'll show you, of course, some examples of how it should look like. Because a Gaussian should not be hard to plot. Have you plotted before using any kind of a program? Or what kind of program do you use to plot? MATLAB? Okay, so MATLAB it is. So plot the Gaussian and then, let's see how the Gaussian, thing looks like. Because so I'm going to just show you. So for instance, so this is how it should look like. Okay, I mean it's and this is the answers, by one of my students from last week. Okay, so you start out with a Gaussian, right? So you start out with a Gaussian. So this is a plot. Okay, the amplitude of the Gaussian field, and this is plotted as you can see as a function of x. So it's in microns. But you see the width of that Gaussian thing? The width of that Gaussian approximately is what? This guy. It's about, I would say, like a 1/3 to a quarter of this entire length. So this works, as you can see. And then typically what he has done, I mean, there are the programs, but I don't want to give you the program. You suffer and do by yourself. Sorry. So, so he has propagated it. So you see here, so it's propagated by a distance of about 0.5 ZR and then 1 times ZR, right? And then 1.5 ZR. Does that make sense? So you need to get the same kind of plots. And you see in all these plots, the graphs are kind of going down to 0 over here. Make sure they go down to 0, because if they don't go down to 0, you have problems. You have this aliasing problem. All right, so make sure of that. Another thing, so here, this guy at 1 times ZR has only gone down to 0.8. Why is that? It have gone down to 0.7, right? Because this is a one-dimensional Gaussian. That's what you are doing. A two-dimensional Gaussian would go down to, like one, yeah, for a two-dimensional Gaussian, the amplitude times the width is a constant. But for a one-dimensional Gaussian, which is more like a cylindrical Gaussian, it's like a squared times w is a constant. So those are details which you should know from Fourier optics or any kind of optics, Gaussian optics, laser optics. So the answer should work out, as you can see. Then the next part here, okay, so you can plot the width of the Gaussian field. How do you find the width? Well, you write a little program that defines, say, whatever point, 1 over e of this, and then, find the distance, half width, whatever, doesn't matter. And then you plot the width, as a function of distance. So this is exactly like what he has done, starting from 10 microns, and as you see, it's increasing. Does this make sense? But I need to see this. So next time, okay, I want some of you to at least show me the beginning parts of plotting and so on. And then the next question, which is got to do with this, say, super Gaussian, right? So the super Gaussian, you see, very small, or can you see? What is the way to blow it up?
It's the plus sign.
Huh? Where is the plus?
Yeah, yeah. Top one.
Here?
Just below that.
Oh, it is. Sorry. Duh. Okay. I'm an expert with computers. So, okay, so as you can see, so here, so this one is starting with a super Gaussian, right? The super Gaussian has the power n equals 2. That means it's like x squared squared. So like x to the power of 4, right? Make sense? So that's why it looks flatter. And the decay is sharper on the sides. Make sense? So that's a super Gaussian with n equals 2. If you have super Gaussian n equals 3, n equals 4, blah, 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 say it is n equals 4, it looks more like a square wave. So then what you're really doing here is showing the diffraction pattern of a square wave, right? That's effectively what you're doing. And so see here for n equals 4, which, is looking almost like a square wave. So after some time, you see at distance about 1.5 times ZR. Well, ZR really does not exist for the super Gaussian, but the same ZR we took for the Gaussian beam. Same distance of propagation. See how this guy is looking like? It's beginning to look like a sinc function, right? As it should be, because the far field diffraction pattern for a square wave is a sinc. Make sense? The other thing that you also see here, this on-axis, the amplitude keeps on increasing for some time before it starts to decrease. That's called on-axis focusing. That's another way you can do lensless focusing just by shaping the beam. And that's very often done in ultrasonics. Okay, when you go to get a sonogram, you don't see a big ultrasonic lens on top of your belly. So the beam is profiled so that it focuses inside. So are you okay with this? So I would like to see some of these. You see, this is done by mortals using a computer. So I would like to see some plots of the Gaussian to start with, and then a little bit about the propagation of that Gaussian, because that will take some time. Okay. Shall we stop for now, or you wanted to start after this, right? Okay.
You all have to solve these problems because that will be the part of the evaluation.
Yeah, at least I should see. Yeah, at least I should see, some attempt.
They have to be graded.
They have to be graded. Okay.
So based on that, we will grade.
And we will use the Goodman's problem of the grade change filter after that. Spatial filtering. No, okay, it will be graded. In Goodman, there is a problem. How by using optical processing, you can change the grade from F to an A. Okay, so that's another way to get an A. All right, thank you very much. So after the break, right, I think Professor Nischal is going to talk about interferometry. So I am going to leave this computer, or do you have something? Then I should leave this. Thank you. So after you have gotten started with this problem, after you have gotten up to a certain point, I want you to also introduce that plane wave, the reference, right? Because you want to write the the hologram. All right, thank you. Well, you're welcome to give me your feedback as well. I mean, feel free to. I mean, if you have, I know some of you have asked for some requests for some reprints of papers and so on. Just send me an email. All right?
Okay.
That's what I do. Okay, I think they know enough about photorefractive. They know enough about the, at least the reconstruction. I have not talked about unwrapping. I'll come to that. Fine. Actually, unwrapping.
Only second day.
Yeah, that's fine. Unwrapping later on, actually, I will also talk about in connection with TIE. TIE. Maybe I should, where is it? Yeah, that's all.
Let it be here. He will come and.
Yeah, but let me take this out because otherwise I'll forget. That's my main problem. I went to that Edinburgh, that Maxwell's place.
Yeah.
These British guys have some weirdo
Yeah,
system.
yes.
Ah, jeez.
I also went to Ireland once for
Ah.
a conference. I had to buy.
I have to buy, yeah. That strange angle
हमारा
stuff.
लैपटॉप लगाना है. We'll have it.
Yeah. Enjoy your tea, onliners.
अच्छा ये वाला इसमें आ रहा है. ये हमारा स्क्रीन को ब्लॉक कर रहा है. ठीक है, ठीक है. कैसे? ये हटेगा नहीं. हैं?
Pointer. Pointer.
ये दिक्कत नहीं है.
ये भी लगा दीजिए कौन नहीं
अच्छा. Okay, so very good evening to one and all. Thank you, sir, for being in the audience. I'm going to talk about holographic interferometry. For last 2 days, you have been hearing the basic aspects of holography and basic stuff. Topics. Holography it's always said that it is a two-step process, like modulation and demodulation, what Yasin sir was telling yesterday. So we have the recording and reconstruction. So what I'm going to talk about, I have taken the sources material from this book, Basics of Holography by Professor Nashwan Adihara. I can share this book. An Indian author migrated to Australia. This book is treated as the Bible in physics. Very good book, very thin book, very comprehensively. What is holographic interferometry? As you know, the interferometry, we all know that you have to have the reference beam and object beam. So like mathematically, we write OXY plus RXY. You take the mod square, you have four terms, mod of OXY plus mod RXY whole square, and plus you have O conjugate R and R conjugate. These are the four terms, but we always achieve. So in holography, we record these interference pattern, those four terms, O cross R, on a film. Or in digital holography, this is what we will be recording on a camera. Now, in the holography, as it is possible that we can capture this wavefront, reconstruct the wavefront at a later time. So, as a result, this interferometric technique can be used to compare two wavefronts. We have one wavefront, we have recorded one wavefront, and we can record another wavefront, and we can compare them. It is basically one interferogram, and you are recording another interferogram, and then you are comparing these two interferograms. So, this originally it is separated in time or space or even wavefronts of different wavelengths. They can be compared. So, since a hologram reconstructs shape of an object with a rough surface faithfully, yes. Right. हाँ So what I have written is that since a hologram reconstructs shape of an object with a rough surface faithfully down to its smallest details, large scale changes in the shape of almost any object can be measured in interferometric techniques. You know the basic approach of this holography for measuring the phase. Talk more on this topic, and in holography, you have only one technique to record phase or to measure phase is the interferometric technique. And this is what is the holography, we measure the phase values. Once you record the phase values, there are some statements I might have talked about, and also said that if you take a hologram, break it into 4 pieces, each piece will give you the same information. Because it is interference pattern. Yes, that could be done. Take a hologram, focus in different regions, and then show you maybe see that you can focus in one simple hologram. You can focus different regions. Similarly, in digital holography, you change the depth of this distance, small d, and you can focus different parts. So here, this holographic interferometry can be used in non-destructive testing, because what is important, we can compare two wavefronts. Holography is all about wavefront measurement, So you can have one wavefront, you can have another wavefront, and then you can compare them. Two fringe patterns, basically comparing two fringe patterns, two interference patterns. Then where we can use them. So application is non-destructive testing. What does it mean, non-destructive testing? Means when you are testing something, when you are measuring something, you are not altering the object. Object is not touched upon. You are simply throwing the light and you are measuring that. So the scattered wave you are capturing. So non-destructive testing, aerodynamics, heat transfer, plasma diagnostics, as well as in the studies of the behavior of anatomical structures, prosthesis and the restless. These are the various applications where it can be used. So what is the basic physics? So first, you should understand what is the basic holography, because these are the equations I will use from there. So simple, this is the off-axis holography. You have the reference wave, here is the object wave, which is at some angle theta. So this is how we represent the simple plane wave reference mean. This represents the object wave. So for recording the interference means we have this Rxy plus Oxy and you take mod square of that. What you record is the intensity. So it is basically mod square. You can write the same thing, Rxy plus Oxy multiplied by conjugate of Rxy plus Oxy. When you multiply these four terms, take mod square. So you have mod square of this one plus mod square of this one, and then you have conjugate of this multiplied by this and conjugate of this multiplied by this. So these are basically the four terms. R square plus O mod square plus RO. These are the phase factors. Then RO and exponential, these are the phase factors. In a way, can be simply written as R square, it can be simply written as OX square, and these are the phase functions. This is what we measure when we record interference pattern. So what does it mean? It means amplitude and phase of the object wave encoded. The amplitude and phase of the object wave have been encoded as amplitude and phase modulation. This is what has been modulated. Of a set of interference ranges equivalent to carrier with a spatial frequency of. Now, what we do, so once you have recorded, this is the recording of the hologram. Once you have done this recording, okay. Now for reconstruction, what we do, we have the four terms. So as we know that for reconstruction, we have to multiply the hologram with the reference wave, or you have to illuminate the hologram with that same reference wave what we have used in the recording. So Rxy we have to again apply. So that will have some transmittance value, and this what is written this term. So this is what we will be obtained when you have we are trying to reconstruct. Second term. So where you have this T naught right? And this term basically a constant background transmittance. It will.
Is the notation same with the
Yeah, same. I have taken the same expressions from that Hariharan's book. So when this hologram is illuminated once again, now we have recorded one hologram. This hologram is going to be illuminated once again with the original reference. So we have one hologram. Now we are illuminating that with the same reference beam. So the complex amplitude of the transmitted wave, what you are going to obtain in the output, this is what will have. Uxy will be Rxy plus Txy. So Txy, I am multiplying with the same reference beam. If you expand, this is what the expression is going to have. So what is real time? What is the application now? This is at the basic what I just said. So what I have said so far, you have R term, reference plus object, added them together and you calculated the intensity. In an optical holography, you are taking the intensity or recording the interference pattern on the film. So you will have basically 4 terms multiplying with that you have recorded once the hologram. Now you are multiplying or eliminating that hologram with the same reference beam again. So if a hologram is replaced, so this is what is basically holographic interferometry. So if you replace that hologram once you have recorded, is replaced in its original position in the same optical system to record it and illuminated with the original reference wave, it reconstructs the original object. Getting my point? Let me read it again. If a hologram, once whatever hologram we have recorded, is replaced in its original position again in the same optical system to record it and illuminate it with the original reference wave, the same RXY, it reconstructs the original object wave. So what? Then the shape of the object, if the shape of the object is changed, like some object has moved or it has been oriented or it has been tilted or anything has happened in between. Any such changes that will reflect into the change in the phase. So it is directly transmitted object will interfere with the reconstructed object to produce the fringe pattern. And this is what is you can see here. So this was the image. It is a deformed object. So whatever deformation has taken place, accordingly you are going to have that changes in the fringe pattern. So we have one hologram recorded. In between something has changed, some deformation has happened. Then you are recording it again, multiplying with the same fringe pattern, same reference speed.
What are these black and white strips?
Yeah, that shows the deformation. It's an object and it is the deformation has taken place. So what we have recorded one interference pattern, then some deformation has happened and you are using the same hologram. So deformation, whatever, how much deformation has happened, that has also been recorded. So you have now two different interference patterns, and that we can compare and come up with the what all has happened, how much was the deformation, how it has happened. So you have two states basically. One state not deformed, second state some deformation has happened. You have one interference pattern, you have another interference, and then you can compare them. Once you compare them, then how much is the deformation that is? Any particular so that depends how much you are measuring. So it depends on application to application. So it has the property you can measure that deformation. That is why these are the applications. So if the changes in shape of the object are small, this is what answers your question. So only phase of the object wave is modified. Complex amplitude and wave from the deformed object can be written as this is the modification in the phase. So you have the OXY and this is the phase change. So now get back to the 4 terms usually written in the book U1 plus U2 and okay. So the first term is there and this plus is the transmittance with the deformation. U2 is this one with the original object wave. So what will happen now? It means now we are having these two wave patterns, wave fronts, and we are adding them together. So you have U1 XY plus U2 XY, and then you are taking modus one. So now this is a new hologram. Started with the one hologram. Now we have one hologram, and with that we have second hologram. Yes.
Here we talk about deformation. So is it the change of the physical shape of the object?
Yeah, physical shape of
we consider the change of the orientation of the object.
Everything. I will show you. There are many geometries where you can use for different types of objects and different cases. So here one deformation I am showing. So now we have 2D wavefronts. Take mod square. So we are having a new hologram now. So if you expand them, this is what the expression we are going for. Here, this beta is negative, so dark fringes are seen. This depends upon this pi xy, how much is the phase. It is twice m pi, where m is an integer. So interference fringes obtained by this technique, it can be used to study changes in the shape of the object in real time. One change I showed that deformation has happened. Any such changes can be observed. So you have to have, basically the simple thing is you are comparing two interference patterns or two holograms. Because the first hologram has the original information from the original aspect, original position, and second one is with the deformation. So how much is the deformation that we can measure? And there is a setup. Now here is the problem that you have to replace that hologram in its original position, and then you have to record another hologram. So that posed a very difficult problem, and this what has been shown here. You can send aside to the reference. The system for real-time holographic interferometry. Hologram is processed in situ, means the same place, and interference fringes are viewed through a CCTV, closed circuit television. Now here what is important, you have to have the hologram, and that hologram has to be in real time reconstructed in it. So that poses the problem, and that creates difficulty, that offers difficulty that what we can do. So it has some disadvantage also, that if you have some intermediate changes, so you have one change, one object is tilted. So in between the tilt, there are some intermediate states. So those intermediate states cannot be measured in this one. One you will measure the initial one and the final one. So there is a disadvantage with this one, but there are techniques how those disadvantages can also be resolved. So this is the real-time holographic interferometry. The recording is the laser. This is the object at rest. You capture the on the photographic plate, and for reconstruction is the developed hologram, and then you can see the deformation in the object. So observer sees any deformation of the object that is in the scale of lambda in terms of wavelength, very minute change. In real time, as interference between real object and holographic image of the object at rest. Is that clear? The basic holographic interferometry, basically which means we are comparing two holograms. One is corresponding to the object in rest position, second one in the object in the deformed position. But what I mentioned here, that intermediate states cannot be measured in this way. We have to have different technique for that. Is that clear? So these are the problems specifically that you have to have replace the films exactly at the same original location. If you do not replace it with the original location, then that will give you a wrong result. Or the measurement what you are going to aim, that will have some disadvantage or difficulty. Film developed at site. Whatever hologram you are recording, that has to be developed at site. You cannot take it to a dark room. So you have different tools and techniques for that. Emulsion pre-swell before exposure. Now here, this can be removed, this technical problem related to the exposure can be removed or overcome with the help of digital holography. In digital holography, you can do the reconstruction in real time. These are the problems with the optical holography, when you are recording on the hologram on a film, and then you are doing that. So it becomes easier when you are comparing and doing it with the digital holography. Digital holography, you can do the reconstruction in real time. There are fast algorithms, and then you can do that. Maybe in one of the lectures I will talk, when I will talk more on the application side, there are some digital holographic microscopes available across the world, commercially available, one can buy. The cost is, of course, very high. costs around I think more than 1.5 crore Indian rupees. I have used the whole the such microscopes. I will show you some results also that can be used for real-time monitoring. And
Is this type of microscope available in India?
no, there is no such microscope available in India. I wanted to buy him at one point of time, but I didn't get the fund. But I have used that the microscopy, and you see very good quality 3D imaging on the screen. It has been used for basically for the cancer cell detection. I have used one in the Finland. Yeah, they have developed a holographic microscopy, but the quality is much different. What is available from the Switzerland.
So in the previous stages, you said that we cannot observe the intermediates.
Yes.
But what if we just take 5 different slides and my deformation has to be gradually shifted? Then we would be able to observe.
Yes, yes. So I have not come to the solution to that problem. I just posed you that these are the problems associated with this one. So to make you understand that what is holographic interferometry. Now then we have another solution, another type of holographic interferometry that we call as the double exposure interferometry. What is this double exposure interferometry? So it is possible to record 2 holograms on same photographic plate. You are not developing the holographic plate. You are recording 2 holograms on the same holographic plates. One of the object in its original state and other of the deformed object. Getting my point? You are recording 2 holograms on the same plate, one of the object in rest, another one with the deformation. So what is the benefit of doing it? Benefit is you don't have to develop the hologram. You can develop once we have recorded both the holograms. So in the previous case I mentioned you have to have developed the hologram. It has to be replaced at the same location and then you have to illuminate it with the reference. So what is done here? Here you don't have to develop them. You are recording 2 holograms together simultaneously on the same photographic plate. One the object in rest, another one with deformation. So this is what we call as the double exposure. So you are exposing the object twice, doubly. One in rest, another one with deformation. Reference beam will be same. You have set everything. You have the object B, reference beam. You have recorded the interference pattern. Now you move the object, whatever deformation you have given. So you can move the object and again same reference beam and record it again on the same hologram. This is what we call as the double exposure interferometry. So the object has been exposed twice. Yes. No, first one is recorded. It is not going to affect that. Now you record the second one. Right?
So even in the primordial case in which the first case, do we need to, is there a compulsion of using the same reference beam?
Yes. It is always compulsion. It is always. It is that compulsion will be removed only when you are using a rainbow hologram or other holograms. There was one just yesterday he got some holograms also in again. Those holograms you can see in the sunlight, but for recording they have used the laser light. For reconstruction, like for seeing the image, you don't need those laser beams. Means you for reconstruction you are able to do with the sunlight or this normal light. So what is happening here? You have this OXY object and deformed object O prime XY, and you are recording this interference pattern. So O prime XY you can write with this one because it has some deformation in terms of the phase. So what would be the intensity? Intensity will be this one. And this.
Some angle used to rotate the deformation.
So that is if in case you are taking the tilt. you are tilting the object, then you have to consider that. Deformation can be of any type. Tilt is a very important or very good application and very useful research topic for the digital holography. If you are tilting the object, how it is going to affect and how you can do that. I'm generally taking some deformation, not talking especially about the tilt. I'll show you one of the examples also. So what will happen in this case? The bright fringes are seen when this phase difference is equal to twice M5, where M is an integer. So double exposure interferometry, it has the advantage that repositioning of hologram is not critical. You are not repositioning that hologram. You are not repositioning. Since two interfering waves are always reconstructed in exact register, in addition, visibility of fringes is good. Since two waves have same polarization and same amplitude, so it gives you better result. It has a common problem again. So what is that common problem? These are what all I am talking. These are all research problems, and there have been research papers to solve them also. So common problem is that if you are using a continuous wave laser, it is unwanted movement of the object between two exposures that poses a problem. So some types of object motion can be eliminated by the laser solution again. This is the problem with the CW laser, how to solve them. So for solution, use the object motion and take the reflected reference beam from a mirror attached to the object, so that compensates the error. Alternate technique is hologram plate can be attached to the object, and the doubly exposed reflection hologram can be again recorded with the object illumination to that hologram plate. So these are the solutions of such problems. It has a disadvantage, again in this case, similar to which is inherent to the holographic interferometry, that information on intermediate states of object is not available. Again, we are taking one state and the initial state and the final state. So in addition, control of fringes to compensate for rigid body motion and avoid ambiguities, these are not possible here. Then in this series, for holographic interferometry, we have a technique called sandwich hologram. It means you are taking two holograms, sandwich them together. You have this object and this is the first exposure. Then you can see some tilt here. This is what you are asking for the angular tilt. So it has been produced some tilt. So you can see the tilt how much. So that is with the second exposure. Now, this is what reconstruction with fringes you can see, and the tilt also. Object tilt compensated, fringe-free reconstruction, what you can see here. So these are different techniques for compensating them in the holographic. Is that clear? One general, very famous kind of picture you will find in the books and Google also. So movement in phase has been contoured using holographic interferometry. Fringe spacing represents a movement of 30 micron and was created by two pulses from a wave laser. Here, a pulse laser was used, not a continuous wave laser. Because continuous wave laser poses that problem. So to solve that, this is what has been used. And the movement is 30 micron. So this is what we can measure with the holographic interferometry.
Possible.
Yes. Yeah, that is a pulse laser. So double exposure holographic interferometry, again, the same thing what I have explained. So two successive holograms, first exposure object is in some reference state. Second exposure object is moved or deformed. And when we talk of deformation, it can be of any type. Tilt, some movement, displacement, everything. So during reconstruction, the two images interfere as though they were two copies of the object. If conditions of at the recordings are different, so interference path between the reconstructed holographic images reveals the deformation. Again, in principle, in nutshell, the whole process, if you try to understand, it is very simple. We have one function, one fringe pattern, another fringe pattern, and you are taking the difference between these. But we have to have this setup to record the interference pattern, and then you are able to calculate that. Yes. More fringes. More fringes is different thing. You have seen that nets in the windows to not allow the mosquitoes to come inside. People use nets. Have you seen them? So you take two pieces of net, one put one over the other and simply change that. You will see a kind of pattern. So that is a kind of Moire pattern. That Moire pattern you can optically generate with the help of this Fresnel diffraction. Solve those problems what Sir was talking for the Fresnel pattern, you will get those Moire patterns. That is again a kind of imaging. That is also the imaging property and generate the image also. So, but that is not the interference pattern. It is simply two patterns overlap each other that creates that kind of pattern. It is not at all interference.
And you can see more in that and also when you record on the CCD.
See what it is. It is not interference. It's not interference.
So the basic condition of interference is not mandatory in the case of modulator.
No, it is not at all interference. So why the conditions of interference will be applied? For interference pattern, of course, the basic interferometry, you have to understand that the two waves to interfere, they should be in the constant phase difference. Then they have to maintain this current monochromatic wavelengths, same state of polarization. That is very important. We have one wavefront, another wavefront. If they are not at same state of polarization, they will never interfere. That is why when we use send information in our fiber optic cables, we are able to send them because two photons never interact. To have interaction, you have lots of conditions. But two electrons, if you want to send, they are going to interact. And this is where the phase photonics has over the electrons. Okay. So these are some more examples of that graphic interferometry. You have this laser light here. You have the reference feed. You create the disturbance, and this is how you can see the patterns and measure them. So what are the geometries? For different kinds of applications, you have to have, and what you want to measure, you have to have different. But one thing is important. This is all important in the optical holography when you want to record it on the film. But the benefit now is in the digital holography, you are not recording anything on the film. So you are recording the interference pattern on the camera, and then you are numerically reconstructing them. So for any kinds of application, what all you want to do, you have to numerically compensate them. Sir was talking in the morning also and afternoon class also that algorithm for reconstruction. You have to have the sampling, write that algorithm for reconstruction. You can create all kinds of holograms. Putting a hologram is the very easiest way to calculate, simply we take the Fourier transform of the object and use the reference mean. I think this also you should take as the assignment for the recording, reconstructing Fourier hologram, reconstructing fractional Fresnel hologram. You can use again fractional Fourier transform and record a fractional hologram like that. So here again you can use different geometries to replace the tape. So during exposure of the double exposure hologram, this is the enlarged view of a portion of the bar showing the displacement in more detail. So how much is the displacement that you can very well measure. So these are the applications where this holographic interferometry is used. So then we have another holographic interferometry that we call as the time average holographic interferometry. What has come? So, anyway, I'll finish quickly. The time average holographic interferometry, this is the vibrating of object here. So what we do here, that hologram is recorded of the vibrating surface with an exposure time which is long compared to the period of vibration. If it is something is vibrating, like you can see this guitar is vibrating. So what has to be done? Exposure time has to be larger, longer than the time of vibration, period of vibration. You can take all, and here you have to do the time average. You have to record many and then you have to average them. Exposure over several time periods. So you have to have exposures on several time periods and then you have to record them. Reconstruction and reconstruction interference of the extremum positions. It is simple to carry out. This is what we call as the time average because you are allowing it for several time periods. That is why it is called time average holographic interferometry. Yeah, nodes. You have created the vibrations. So again, one in the rest, another one is in the deform. So this vibration again is a kind of deformation. You are listening good music, but it's a kind of deformation because it was in the rest and you have deformed it. Oh, that is all. I'll stop here. Well, has got any questions?
In the last image, so that essentially depends on which string type plug.
Yes, yes. Of course. This is a very famous picture you will see in many books. This one. This is the one. So I'll continue more on this holographic interferometry tomorrow, and then tomorrow we'll start the phase shifting. That I've already introduced the topic. So then my more stress will be on the application part of the holography, of the digital holography. Then more basics from sir, I will talk more on the applications part. Okay.
And I will also maybe tomorrow after finish this part, I will also show similar application but using.
Yes.
So if you use photography, so you can also do this. So again, deformation of an aircraft, wind tunnel. It's a practical. I'll show you something.
तो आप आ जाइए मैं जाऊँ ये लोग टायर्ड हो गए होंगे पानी क्यों दे रहे हैं लोग They have come here to be tired.
Yes, yes, yes. And our duty is to make you tired.
So there was a method which was traditional charge method, where some dust particle was used to get this nodes and anti-nodes to violin, I think, before this holographic interferometry technology. Whenever holographic technology came into the Then foreigners they started with guitars, violins, and other instruments. And in India, Dr. P.T. Ajit Kumar from CUSAT, Question he has a company which is Light Logics. Yeah. It's not from CUSAT, a student of EADR.
Yeah, he runs his industry in Kerala.
Kerala. He studied the antinos of Indian flutes, Hindustan classical. But I don't know how they are. If I will know about details,
So you have to record the holograms. You have to record the holograms. What I mentioned in the beginning, that leave the meeting. Okay, you have to join the meeting.
वो लिंक भेज रहा है आपको।
नहीं मैं हटा दूंगा तभी तो आप उठिएगा। So the simple way is to record one pattern, then you record second pattern. Second is the deformation. Deformation can be of any type, like tilt, some movement, some vibration, these are all deformation. This is how you.
After getting this image, how this image is studied, to
So
know about the materialistic properties of that musical instrument.
No.
ये मैं वाईफाई में चला गया
How much is the deformation? So that has to be connected with the actual nodes and antennas. So there is connection. These are all depending on the phase. Like you must have done the sonometer experiment. So in sonometer experiment, you will create the standing wave, and that creates nodes and antinodes. There you will study them. So it depends upon the phase distortion. And here we are measuring that phase information. What distortion we are measuring, it is in terms of phase. So the moment we have that phase information, it means we can characterize the whole thing. The phase information, otherwise you don't have, you cannot create. Yeah. Yes. Speckles is inherent. The moment you use a laser light, speckles is inherent. Speckles
1 घंटा
1 घंटा
ज्यादा लेंगे? आप ज्यादा बोलेंगे लोअर साइड में थोड़ा सा मुश्किल है, अपर साइड में पॉसिबल है।
You can compress it.
Yeah, after compressing only it is 1 hour.
Oh.
No, I'll try to do it. Maybe 5 minutes before that.
हो गया कनेक्ट
सर इसको भी करना पड़ेगा ना सर, 1 मिनट सर, इसको भी करना पड़ेगा।
Yeah, let me see that how fast I can go. But this time is for network, not mine, okay? My time has not started yet.
Oh, yes, sir.
You-
We didn't start the timer.
Right?
This is the unofficial tea break between lectures.
Tea break? Tea break?
Yeah, we generally get tea break after each lecture, so this is what's going on.
Okay.
That's what you're saying, it is unofficial tea break.
No, no, we shall do it.
Without tea.
Without tea.
Yeah, like the government.
Tea break to water break.
But I had tea, no? There are some few cups left. I have taken.
सर यहाँ रिकॉर्ड हो रहा है ना।
अच्छा, ऑनलाइन में कितना है भानवी जी?
हाँ
नीरज कितने लोग हैं?
सर वो खड़गपुर से भी जाता है ना।
यार हाँ समझ गए, यहाँ से करते हैं और ये यहाँ पे करते हैं और यहाँ से ये जो रिकॉर्ड हो रहा है
क्वारंटाइन करते हैं,
मतलब है
इसका क्वारंटाइन वेट करते हैं।
तो ये जो ये है ये डेटा सेव हो गई। नहीं तो मेरा भी ट्राई कर सकता हूँ हॉटस्पॉट में। अच्छा करो ठीक, मेरा फोन से भी हो सकता है, देखो कौन जो भी है।
I was going to introduce myself. I'm Parthik.
Yeah, I know that.
I might be for some time just because I wanted to read.
I've been giving.
That's fine, but I want to see the introduction when I was here.
Yeah.
Thank you.
We'll definitely meet again.
You will.
All right, so yeah.
क्या नहीं कनेक्ट हो रहा है?
सर हो गया।
हो गया। हो रहा तो ऑफलाइन में तो करेक्टेड है।
हाँ इधर आ गया, अभी ऑनलाइन में जा रहा है ना, ऑनलाइन में भी इको हो रहा है। ठीक है ना?
आपका कैमरा प्रॉपर्ली ये कैमरा चलेगा। So let me introduce
and how you understand a physical system. Okay, so calculating and deriving the things are not enough. When you apply it to a physical system, that's the most difficult part of it. So you have to understand the physical system, you have to handle the physical system for application. So actually, there is a delay in time. But somewhere there's a Nobel Prize in the works related to quantum physics. They are Nobel laureates. Okay, so I have listed up to 2015. So there are, I have counted, till 2022, there are around 75 Nobel laureates who have gotten Nobel Prizes for discovering different effects in quantum mechanics and also the kind of interpretation of quantum mechanics. Okay, so I'll go ahead. I'll touch upon some of them. Okay, this is one of them. Harrows and Wineland. I'll touch upon this. So, whatever no, so no, no. is, so all over the world, people have been, let me change the slide as soon as possible so that it comes here. Yeah. Yes, yes. Good. So this is the curve I was talking about. So different parameters are kind of saturating, and then that is why all over the world you can see it's a quantum effort, because everyone, all countries, they want that the second quantum reduction should come faster. Otherwise, we cannot get better technology. Okay, so that's the situation. You can see that total effort is $30 billion, not rupees, and and you can see more or less the contribution from different countries. Yes, yes, thank you. But then especially you see China, $15 billion. Okay, and then also India. India says that they've spent $1 billion towards quantum technology. Okay. So now this is the quotation from nobelprize.org for this year's Nobel Prize 2020. These were shared between three people, Clauser, Alan Specht, and Jaliger, a few of them. So for the contributions of proving quantum entanglement in different aspects, and also to implement quantum communication. I'll come to those things. You can see the quotation is, it has become increasingly clear that a new kind of quantum technology is emerging. We can see that the laureates' work with entangled state is of great importance, even beyond the fundamental questions about the interpretation of quantum mechanics. Okay. So now the thing is, what is quantum entanglement? You know that quantum system has something called wave function, which can describe the whole system, right? Now, say by the word, English word entanglement, I mean that you have two loops, they're separated. If I make a loop like this, right, you cannot separate. Then we call it as entangled. We cannot separate. So it is more or less the same meaning which you use in quantum mechanics, but physically it is completely different thing. Why it is different? I say, so these are the very famous characters, Alice and Bob. Okay, and they have their own atoms. Alice has her own atom. Bob has his own atom. And then the wave function of the atom 1 is psi 1. Wave function of the atom 2, Bob, is psi 2. Now they come closer and then create entangled state between the atoms. Entangled state. Now, for these loops, you don't take this loop away, right? But after entanglement, Alice can carry her atom and go to USA. Bob can carry his atom and remain in India, stay back in India. So they can be far apart, in the opposite side of the earth, but then still the common state of these two atoms will be entangled. That's the kind of surprising thing for quantum entanglement. It's very surprising. The things are apart indefinitely, maybe infinity distance, but then these two atoms are correlated. So if I talk to this atom, so A mera secret hai, mat batana, other atom will come to know. Okay? So this is how they have a correlations, and you do something on this atom, other atom will come to know. Well, so this is like you always hear about spin, and so on. So Alice has a both spin up and down, and so they share the entangled state. If you measure up spin for Alice, automatically it will be a down spin if it is so, like it is conditional measurements, but then they are far apart. One is at USA, another is at India. So what I said just now is that the wave function of Alice is psi 1, wave function of Bob is psi 2. Initially, they are not entangled, so you can write as a product. Okay? If they are entangled, you cannot write as a product. Product means the wave function of Alice multiplied by the wave function of Bob. This is not possible. Why it is not possible? Because of this summation. Psi1, Psi2 plus Psi2, Psi1 and so on. So you cannot write as a product of two wave functions, and so they are entangled. So you cannot separate it out. Okay, and this becomes the common wave function. Okay, if they are entangled. And this is again another surprising thing. So what is written here? Entangled pair 1, entangled pair 2. So this device, I'll come to this device when I come to the application. But imagine that I have a device which can make entangled photons. Okay, so two photons are emerging, they are entangled. So here for this device, you have 1 and 2 photons. Here it is 3 and 4. Just leveling 1, 2, 3, 4. That's all. But then these two photons are actually again made entangled by some another device here. You know what happens? Automatically these 1 and 4 will get entangled. And these two photons have no relation with this device and this process. They are completely independent. So, but they'll become entangled. So it is a full of surprises that this happens in quantum systems, and that is why it is so difficult to apply in physical system, because you don't see these systems in reality. Okay, if I just leave this pointer, it will fall down. I don't have to understand that what is the effect of gravity. In the childhood, if somebody says, okay, that earth is pulling it, I'll understand in one sentence, because I'm looking at it since my child. But in quantum physics, the applications you don't see around it. This is another thing, that understanding it intuitively is not so easy. Well, now, as I said, is the product state psi phi, and is psi of phi, and then I'll go ahead to have entangled state. Now, if I ask you that, so this is the total state. If I ask you, can you write this as the wave function of Alice multiplied by the wave function of Bob? Then it is not possible, right? So this is probably quite obvious. You cannot write as a product. It is a product plus product. Okay, so you cannot separate them as a multiplication of one function by another. Now the question is, so what is this entanglement good for? I understand, okay, this entanglement is there, and two atoms, two quantum systems, they are entangled, they are correlated. Now, what is this good for? So now they go to, Bob goes to USA and it stays back. Now the question is, can I send? Because it is correlated, I understand what is going on to the other side. Can they send a quantum information from Alice to Bob? Sending which information? Quantum information. WhatsApp chatting name. Quantum information. So some information in the form of quantum wave function. The answer is yes. That is again, this is the contribution by Zeilinger. Zeilinger has done a series of experiments. Even today also he is doing experiments, lot of experiments, that to show, to demonstrate that teleportation is very much possible in a large scale. Okay, so this state is a completely different state from this one, but because of this correlation, this state goes to Bob without doing anything, without passing the information from here to Bob. So information I don't have to carry, the Alice doesn't have to travel to Bob, so nothing should be done, and then the information will go to the other side. And this happens. So this is called quantum teleportation. Teleporting means sending one thing from one place to another, quantum teleportation. Now this is, you'll be happy to know that this is not in the level of theory. China has launched satellite several years back, quantum satellite, not normal satellite, quantum satellite, and then sending the quantum information. So now in today's time, there are 2,500 kilometers is the range of quantum teleportation. How much is 2,500 kilometers from one side of India to another side? And from Europe, because India is a very big country, from Europe you can send from one country to another. Okay, so this is the range that people have been doing quantum teleportations. But then you have to ask me that why then it is not happening, why you are not applying in our daily life, right? So for that you have to have quantum devices. Okay, so implementing it, see, that is the second quantum revolution we are talking about. You have to have technology in your daily life. You have, definitely you have your mobile is having GPS. The GPS runs with the atomic clock, which is quantum mechanics. Okay, so this is the time which is measured in Delhi NPL by atomic clocks. Atomic clock is a quantum based clock. So it has been going on since years, but then that device has to come to your mobile. That is the difficult part, right? Well, now the thing is whether China only can do it or we can also do something. Yes, you all of you can do that. Students can do that. And hands-on, then how entangled state is looking like, what may be the circuit, like you can play around in quantum computer of IBM, not ours. IBM has different categories of quantum computers, and the experiences of quantum computers are stored, and that gives you different kind of hands-on thing. Is free. This IBM QSkit simulator you can actually download. Is a free software, and then you can actually have you can build up the circuit. So this circuit, so there are gates, logic gates. You have heard about logic gates. If you have read electronics, right? Different logic gates. So these are quantum logic gates. This is for quantum circuit. Okay, Hadamard say in classical computation, electronics, what are the gates you have? Can we name some gates? AND gate, OR gate, NAND gate, and so on, right? Similarly, you have to define logic gate in quantum mechanics. So this is one of them, Hadamard. This is C0, and these two combination can give you an entangled state. Zero, say Q0 and Q1, they are input. If Q0 is 0, Q1 is 0, then you'll get 0, 0 plus 1, 1. I have written it in a larger font so that things get enhanced. So 0, 0 plus 1, 1. So this is entangled. So initially you have 0, 0, 0 multiplied by 0. Imagine that this is Alice qubit and this is box qubit. Then it is multiplied 0, 0. But then after this, if you have a measurements here, before measurement, this is the state. Now, what IBM this QSkit does, that they do projective measurements which relies on probabilities. Okay, if you cannot read it, I'll read for you 0.495 and 5.0505. So that says that more or less equal probability for 0, 0 part and 1, 1 parts. That is why you can see 1 upon root 3 there. So this is the simulation in quantum computer. And similar thing you can also do it for teleportation. Okay, so like you have to know the circuit, how is the circuit works. So this is Q1 and Q2. These two are the two qubits, one qubit for Alice, one qubit for Bob. And this is the qubit which, that is the information which Alice wants to send to Bob. This information has to be sent to the other side. Okay, so this is the information here, Q0, that has to be sent to Bob. So it has to come to this channel, right? This has to come here. And so what it does that, there is some entanglement. This circuit is shown to you from the previous slide. So this is what it entangles these two channels, and then you operate C0 and have Hadamard again. So what you get is you have a conditional measurements here. The devices, measurement devices. क्या हो गया? Oh, I think so now so then if you measure, then this information will directly go to Bob. So where is this circuit now? This circuit is with Alice. Alice is in India. So Alice has built up this circuit. Bob doesn't have this circuit. Now Alice has to make a phone call to Bob by saying that if you get this state, you operate this. If you get this state, you operate this. If you get this state, you operate this. Then Bob will just measure once, just operate matrix manipulation, no quantum measurements. In pen and paper, he can do that, and then we'll get the actual state. So this is how it goes on. So this is, I'm not getting into this sphere. This is the block sphere where the qubits are represented. So this is actually coming to Bob, and this one are the qubits to Alice. These two. and then you can have measurements. If it is 1, 1, you have to measure, the Bob has to measure, so it is the Bob, X and Z. So they are again two logic gate. So again, so this is quantum teleportation. ऊपर ऊपर हो गया, अभी अंदर जाएंगे, ठीक है? So how to start with this? How to learn that, how to build up things? Again, I will not get into detailed formalism of this, but at least your known thing, कुछ भी होता है oscillator, सब लोग बोलते हैं pendulum, spring, इसी से start होता है, right? So is a classical oscillator. किसी का नींद आ रहा है, सोना नहीं है, ठीक है? Okay. So this is the spring, and you know they are oscillating, but you know this is the starting point of any physical system. Most of the physical systems is an appropriate model for applying to any technology, even for classical systems. But for quantum systems, we have to go to a quantum version. So how we can go? You know, in quantum version, things have to be represented by operators. P square by 2m is kinetic energy, this is the potential energy. So these are Hamiltonian. And then you have, in quantum mechanics, you have levels, right? Energy levels. Now, who takes care of the transition from one level to another? Who takes care? Mathematically, this A and A dash. है ना? याद है ना? Okay. So then this is the Hamiltonian. It is my duty to show some of the basic mathematics. Unless you ask me, I will not get into this explanation. So this is energy, which is the measurable quantity. Now I'm talking about the eigenfunction, eigenenergy, which everyone looks for. So this is the eigenenergy for nth level. This is the wave function of the nth level of what? Of harmonic oscillator. What kind of harmonic oscillator? Quantum. Now, as I said, the quantum harmonic oscillator is the building block of quantum information. So quantum harmonic oscillator ho gaya. Now you have to ask me, so what is quantum information then? Okay, so let me get into this. For that, you have to know this. So this is the one taken from Wikipedia, and you see this one, right column only. That will be enough for me. So this is kind of a spring, but this I'll come back later. These are the eigenfunctions. Okay, so if you superpose eigenfunctions, look at the bottom one, this and this. Can you look at these two together more or less with your third eyes? So this position is moving like this, the spring above. So it means that your eigenfunctions psi1, psi2, psi3, psi4. But then if you superpose, you are more or less having an idea that how a particle can move. That's a classical oscillator. This is quantum. So you can more or less have some analogy if you superpose eigenfunctions, right? So this is the easiest way I could show you. Okay, this is the phase. I will come back later. Now, how to represent particle in quantum world? Say, why particle? Because you have to, whatever you do, you'll be playing around with the information, quantum information, quantum particles. Now, quantum is probabilistic. Now, where is the particle? So that's a difficult concept, of course. So let me just tell you in an easy manner how the particle concept came in. So Schrodinger, long back in 1926, you can imagine, he has said that harmonic oscillator, wave packet. Packet means something together, right? Packets. So wave function, if you superpose wave functions, they create packets. So the packets, wave packets of harmonic oscillator, they behave like particles. Okay, non-spreading wave packet of harmonic oscillator. This was the statement, if you translate, non-spreading wave packet of quantum harmonic oscillator. That we should behave like a particle, and this is named as coherent state later. He did not name as coherent state, but it was a coherent state which was named later. But then the word coherent is a very difficult concept in quantum mechanics. In optics, what is the meaning of coherence? All of you know, or some of you know? So different definitions are coming even for classical optics. So you have spatial coherence, you have temporal coherence. Okay. So in optics, it is well known. Everybody knows that. Now in quantum mechanics, the problem is that this coherence, how a particle, quantum particle here and quantum particle here, can they create a coherent superpositions? Can they combine coherently? Coherently, this adverb is the one which has to be understood. So the laser, which you see everywhere, this one, Anna, this is a very localized light, different from this tube lights, right? Why it is so localized? What kind of coherence? So laser coherence is not easy job to understand. So then you have to get into correlations in semi-classical quantum physics, because laser is an object which is also modeled by this coherence harmonic oscillator coherence state. Quantum model of laser, it matches perfectly. Okay? R.J. Glover got the Nobel Prize for this. Okay, so I met him in 2009. He got Nobel Prize in 2005. So what he did in 1963, he had back-to-back papers. Also, ECG Sudarshan together, that how coherence in optics, semi-classical optics in quantum mechanics should be understood. So it's not like spatial coherence, temporal coherence. There are degree of coherences, correlations. The coherence depends on correlations. Whenever this Gyan course started, all of you have come from different parts of the country. Then when you spend couple of days, then you have a coherence. So that correlations, interactions make things coherent. So that is what he said, and with formalism and lot of complicated structures. It is not very easy to understand. Now, what is coherent state then? How to construct, formulate a coherent state? I know wave function of a system, but these are the definitions: annihilation operator, displacement operator, minimum uncertainty coherent states. Okay, so this is some mathematical formulation which are very well established, and now this is how it looks like. Okay, so this is the phase space x and p, and this is x, this is p. It's a phase space. How does a classical oscillator move in phase space? Any idea? Classical oscillator in phase space, in x it oscillates, in p it oscillates, then it is a subtext, right? Sine square plus cos square is 1. So if this oscillation is cos square, that oscillation will be sine square. The same thing you see here, they are moving in a circle. This is the bird's eye view of coherent state. It will rotate like this, it will form a circle. Okay, so that is why you see they are not decaying. It's a quantum wave packet. This is no more classical, just like a laser. Now this one is almost moving like a classical particle, but classical particle will be a point, but here you have probability. You see, there is a Gaussian kind of probabilities over there. So these are some interesting things to observe. Now just look at a Gaussian wave packet, not a coherent state, any other wave packet. See it decay. Yes. So it is almost kind of decay to a useless one. So this is about a non-coherent. It is also a coherent superposition, but the coherent, I mean the coherent which R.J. Glover has said, is a quantum coherence has to be there. So it has to be coherent state. Now this coherent state, as I said, it will look like this, right? So this is a x is oscillating over x, just like a pendulum. Is a non-decaying wave packet. You can also have other kind of wave packet. It is resolution is very bad. Okay. So this squeeze state, you see, they are squeezed, but they are also non-decaying. So this wave packet is also kind of very much useful in quantum information science. So these are the wave packets you create by optics, you create by atoms. Okay. and they use the quantum information. Now you see the supervision. Is a wave packet of Rydberg atom. And you see how what it happens. It decays. It decays. Then you see some peaks. Let us count the peaks. It is 8, almost 8 maybe. It's changing now to 6. Right? You see clear peaks. Right? And the number of peaks, there's 4 now. Right? So it looks like the 3, now it will come to 2. So different numbers at different time. You see time is running here. Now different time, different numbers of wave packets. These wave packets are just like a replica of the initial one. These are the fractional revivables. Because it is a replica of the initial one, so it is reviving. But in fractions, earlier it is a 3 parts, then this one will be 1/3 probability, right? 1/3. So that is why they are smaller. Is a 2, this is because it is the half of the revivable particle. This was the fractional revival. Now, this is enough for me to get into applications. So I'll actually, start with this. Hope you are not tired. How much time I have spent? कितना हुआ? 20 मिनट? 40 minutes हो गया? ठीक है, 20 मिनट में कर दूँ. But are you getting it interesting or not?
Yes.
That yes takes me to extend it a little bit more. No, just kidding. So let me tell you some applications not borrowed from somewhere else, whatever we are doing, but making it a easier form. I cannot get into the application, things are not very trivial. Now, two most important what I can say, that features of quantum mechanics, which makes it so different from classical world, and people are looking for quantum technology. So first is superposition, quantum superposition. अभी बोलोगे सर ये नया क्या है? ये तो वाटर में भी होता है ना, लाइट में होता है, डबल स्लिट होता है. The first thing you learn that you see, any pond anywhere around your home, you see there are superpositions happening, waters are coming and superposing, there are ripples, interference patterns, right? These are very common. Then when you start reading textbooks, you see the interferences of optics, right? Double slit experiment. So those are the things, even if you don't see the experimental setup, you can understand, right? The photographic plate will have maximum minimum. Now, what is quantum superposition? In classical superposition, even if it may be optics, maybe mechanical wave, the two waves, okay, separated, they have to come one above another. It may be water, it may be any wave, right? Light wave, anything. It will come one above another. For quantum, two particles doing nothing. There is a superposition in between. This is called non-local superposition. Non-local superposition. It's very different from classical superposition. You have to understand this point first. Okay, the difference between classical superposition and quantum superposition. So quantum superposition makes it so viable and important. So it also kind of brings you to precision measurements. Let me just give you some example by introducing Schrodinger cat state. ये Schrodinger cat is very famous. ये सबका कैप में अपीयर होता है, टी शर्ट में अपीयर होता है ना? But what is it? है ना? Schrodinger के अलग से cat था. So let me not read this one. Let me go to the next slide. So this was a thought experiment of Schrodinger. So there was a debate by Schrodinger and Born, Max Born, all Nobel laureates, high level discussion. And so Born said that Born was in favor of probabilistic concept of quantum mechanics. And Schrodinger was not in favor. Schrodinger was not against quantum mechanics. He was supporting quantum mechanics, discovering things, but then it is a kind of a debate between the interpretations. Born says, okay, I think it should happen. Schrodinger said, no, it should not happen. Something like that. It's a high level of discussion. And then Schrodinger thought, Born is not understanding my point. So let me describe some thought experiment. Thought experiment क्या होता है? Experiment करेंगे नहीं, सोचेंगे. है ना? एक एग्जांपल, कोई भी एग्जांपल हो सकता है? नॉर्मल, हाँ नहीं नहीं, नॉर्मल में, नॉर्मल में कैन यू डू सम थॉट एक्सपेरिमेंट? ठीक है, बिल्कुल एकदम करेक्ट। पानी अगर पियोगे प्यास हो जाएगा, वो पीने का जरूरत नहीं है ना? किसी को मारेंगे तो लगेगा। ये ऑब्वियस है, दीज आर थॉट एक्सपेरिमेंट, मारने का जरूरत नहीं है ना? हम डरते हैं ना, बेटा को बोलते तुम कितना मारेंगे ना, तो उतना काफी है मारने। वो सोच रहा है कि हम पापा अगर मारेंगे तो लगेगा, वो थॉट एक्सपेरिमेंट हो गया है ना? सो शॉर्टिंग थॉट एक्सपेरिमेंट कैसे किया? ओके, सो इट इज अ बॉक्स. Now he imagines that there is a cat, and all of you know radioactive decay. So there's something, this is the symbol for radioactive decay. Some radioactive element is kept there. Now the apparatus is such that if there is a decay, then this hammer will fall to this beaker. Beaker में क्या है? Poison. Okay. So if there is a decay, the hammer will fall, the beaker will break, poison will come out, cat will die. ठीक है? शॉर्टकट करते हैं. If there is a decay, cat will die. है ना? If there is no decay, cat will be alive. Clear? अभी this decay is spontaneous, right? It is spontaneous. You don't have any control. Radioactive decay is spontaneous decay from the nucleus. Now this is the probabilistic. Now Schrodinger says, okay, so because it is probabilistic, so do you say that the cat is in a superposition state of dead and alive? That's not possible. The cat will be either dead or alive. He said, because the cat cannot be in a superposition state of dead and alive, so quantum probability is not possible. It is not a probabilistic theory. So that was his argument. Before telling to Bond's thing, I have to also tell you a very simple way of telling quantum measurements. Okay, basket of cherry. Now we read this. Macroscopic what? These are macroscopic. है basket of cherries, many of them more or less identical. Assume them identical. We can see them and test others. है ना? उसमें से एक लेके हम टेस्ट करेंगे तो एक बास्केट फुल ऑफ चेरीज रहेगा ना? सो आई कैन टेस्ट देम एज वेल एज दे आर आल्सो देयर. खत्म नहीं हो रहा, राइट? So cherries are both red and good. You can see them red and also taste it simultaneously. Red, good, दोनों एक साथ. अभी चलते हैं क्वांटम वर्ल्ड में, माइक्रोस्कोपिक में चलते हैं. एक ही चेरी है ना? ये माइक्रोस्कोपिक नहीं, जस्ट काइंड ऑफ लेमन एग्जांपल. So either you look at it or you eat it at one time. दोनों एक साथ नहीं कर सकते, खाओगे नहीं तो देखोगे. So the thing is, the cherry could not be good and red at the same time. Okay? So this is about a easy way to understand quantum measurements. Quantum measurement में क्या होता है? हम चेरी को देखे तो टेस्ट पता नहीं, वो रेड है, so I'll only say it is red, so collapsed. The properties of cherries are red by looking and probably sweet by eating. दोनों properties है, but you don't know what is the taste because you are looking at it. So quantum measurements, whenever you measure, it collapses. The wave function collapses. Okay, so this is how it happens. Now what happens to Born interpretation? Max Born said against Einstein's thought experiments. Is the live cat, dead cat. He said that yes, they are in a superposition state inside the box. Inside the box is closed. Now if you open it, what you'll see? Either it is dead or open, so you are actually measuring it. When you measure, it collapses to what of the state? Either dead or alive. But cat quantum particle nahi hai. This was just a example and kind of arguments went on. But then let us come to quantum system. Same thing. One coherent state, constant from top, it will be circle. One circle, another coherent state. Is a live cat, dead cat. Let us assume it is a live cat and dead cat. Both of them are live, they can move, but then let us name it as live cat, dead cat. Now, according to quantum mechanics, as I said, there can be quantum interference in between the space. They don't have to come one above another, right? So this is what happens, and then you can also kind of rotate it, and you can do many things. So this quantity, one block of it, two coherent state and superposition, is called Schrodinger cat. Schrodinger cat. So Schrodinger did not discover it, but because of his famous experiments, yes. So this was named by his name.
Cherry वाला जो आपने एग्जांपल दिया उसमें थोड़ा सा मतलब कंफ्यूजन है.
Okay.
लाइक आपने कहा कि रेड और टेस्टी. ओके. क्योंकि हम लोग दो अलग-अलग प्रॉपर्टी को कंपेयर करें इसलिए ये बात कहते हैं. अगर हम ये कहेंगे कि चेरी रेड है तो ब्लैक नहीं होगा. या वो स्वीट है तो साल्टी नहीं होगा. सेम प्रॉपर्टी जब हम मेजर कर रहे हैं तब हम ये कंडीशन लगा सकते हैं. प्रॉपर्टी डिफरेंट जब मेजर कर रहे हैं तब ये कंडीशन कैसे लगा.
अच्छा, फर्स्ट ऑफ ऑल इसमें हम लोग डिस्कस नहीं करेंगे बिकॉज चेरी इज नॉट क्वांटम.
हाँ, उसमें एक बात करें, हम लोग प्रॉपर्टी की बात करें.
Yes.
एटलीस्ट यहाँ
So the idea was cherry has both the properties.
both the property
It can have n number of properties.
yeah both are
Okay.
different, like color is the
जो देखोगे बस उतना मिलेगा.
like यहाँ पे लाइव और डेड जो है ये एक प्रॉपर्टी का उसका दो पार्ट है.
No, it is not. It is not.
This is mutually exclusive.
So these two, okay, so this is one coherent state, the coherent state which I described, one wave packet, and this is a separate wave packet, nothing to do with this, nothing to do with this, two different wave packets, two state. वो जो कैट का है, चेरी का है, वो क्वांटम पार्टिकल्स नहीं है. But why Schrodinger has said in that way? Because that time it was not so easy to tell in terms of wave functions. So he wanted to say that quantum superposition is not possible. Because in between, you cannot have probabilities. If the particle is here, it is only here. If the particle is here, it is only here. But here it says that no, you can have the particle somewhere here also because you have some probabilities, which is coming from interferences. Right. So basically, there are different kind of measures. That is one of the measures of coherence. Different kind of measures of coherence. As I said, the coherence is not, say I have two electric fields, okay, and when I can say that these two are correlated or coherent, okay, so I have to actually find out their overlap divided by something complicated things, and then I can find out their correlations. From the correlation parameter, I can interpret whether their coherence is first order coherence, second order coherence, and so on. Okay, for example, laser is also electromagnetic wave, a coherent electromagnetic wave. So for laser, the first order coherence is 1, which is maximum. Second order coherence is again 1, maximum. So it's a highly coherent object. Okay, so there are different measures of coherence. Okay, so there are n number of measures of coherence. Yeah, right. So autocorrelation is that how things are correlated. Say I have two things. Sometimes it causes a fidelity, sometimes autocorrelation. So how they are correlated, whether they are kind of having a similar, they are staying on the same place or different place and so on. So okay, so the correlation, classical correlation is also possible, right? The two magnets, south pole and north pole, they are attracting because of correlation. Right, magnetic effects, electric effects, and a lot of things, right? But then we are talking about quantum correlation. Now, quantum correlation, you are partially right because there is a gray area from classical to quantum. I'll talk about some of the things briefly, very briefly. This area, gray area, how to define correlation here. Okay, so this is called a semi-classical approach. And that's why Glover has got the Nobel Prize. He has talked about the semi-classical system as well as quantum system, both. I'll come to one or two examples. You can see that. Yes, sometimes, yes. Sometimes, okay. So, yeah, so let us take one Schrodinger cat. So, Schrodinger cat is altogether the whole thing, live cat, dead cat, and superposition, right? Inside the box, it was in a superposition state. So now if you just take the middle part, interferences, And then you can see that how they look like, coordinate and momentum space. And this blue lines, you can see the blue lines. So these are minima. A red line is a maximum. So it's highly oscillating structure, and these structures actually is very useful for sensing application. What is sensing application? Sensing, sensor. Different kind of sensors are there, right? What sensor does? Huh? So sensor identifies any change, right? A small change of anything, say temperature sensor, could change hota hai. Suddenly, the sensor says that there is a change. Now, how a better sensor, a sophisticated sensor will identify a very small change. Right? So this is called quantum sensing. Because quantum particles are very small, particles, this table can be described by quantum mechanics, and there I have to go to the atomic scale, I have to model to describe the macroscopic object. But the description starts from quantum objects, quantum levels, right? So when you think about quantum levels, say there is no board, but imagine there is a chalk dust. कितना छोटा होता है? बहुत छोटा, right? Now I ask you, can you move this one dust by half a millimeter by your finger? You cannot do this. It will be always 2 millimeter. नहीं तो नहीं move होगा, right? Or it's very difficult. Why? Because your finger is dimension of the finger is much larger than the dust particle, right? So if this is a common sense that if the entity is very small, you need a very fine thing to move it. No? So because quantum system deals with smaller things, microscopic objects most of the times, so the measurements are small quantities should be better in quantum physics, right? This is a common sense. So I'm just interpreting without knowing anything. But now it is true because these interference structures will give you a much better sensor. Okay. So now some examples. Schrodinger cat mathematically looks like this. This is a compass state. Let us see that how they look like. This is a Schrodinger cat. Now it is a compass state. Compass means it shows the direction. North, south, east, west. Right? There are 4 states, and they actually give north, south, east, west. And see the middle. Middle is a kind of a checkerboard. And each structure, red is a very small one. Very small. It's a much less than Planck constant. Uncertainty, minimum uncertainty is Planck constant. Much less than that. Say 1/20th of that is so small. Now, if you use this structure, you will be able to measure a very small distance, very small momentum, and so on, phase, and so on. Right? So this is called the field called quantum metrology. Metrology is the field which measures different things. Right? Like how do I know that something is 1 centimeter? How do I know? In the class 8 or so or 7, when we learn about the units and dimension, we learn what is the definition of centimeter. France में lab में इधर रखा है, temperature है, pressure and so on, right? So if define, so 1 centimeter is same for everyone in the world, right? So now if you say I say that this is कितना होगा 6 inch, है ना, 6 inch, but is it exactly 6 inch? Then how do you know? You have to measure by scale. Scale रखोगे. How do you know that scale is exactly falling on the edge? Scale का जो line है उसका width है ना, fraction of millimeter. So all these things by your observation, your apparatus, your kind of sophistication, everything makes it inaccurate measurements. Okay, and that is why it is a fixed scale. किसी का नींद आ रहा है, सोना नहीं है. Okay, so there is a fixed definition of centimeter, है ना, meter, second, everything. So these are universally correct. So these definitions are actually redefined in quantum mechanics. That is also another Nobel Prize. I'm not getting into those things. So north, south, east, west. Now you can have several of them. and can have quantum information. I'll come to those things later. Now coming to, like she has mentioned, this is the application number 2. I'll be very brief in saying that unless you ask questions. I'll try to explain in an easier way so that I don't get into the difficult part. So condensation of photon difference. So there are two things actually. And what is this? What is this? You have to correlate with the previous slide. Nothing I am showing which I have not shown earlier. So combination of coherent states. All these dots are blocks are coherent states situated in a circle. Now there are two situations. One is distinguishable. है ना? Distinguishable. If two wave packets are distinguishable, ऐसे होगा तो पता नहीं चलेगा. ऐसे होगा नहीं पता चलेगा. So one maxima should fall under minima. You know Rayleigh criteria. That's the kind of thing, you know, applicable to all kinds of wave. So then if they are distinguishable, then they follow classical diffraction limit. We have shown that. So it's a classical optics. If you have a ring source, you probably, you know, in textbooks, in advanced textbooks, you will have a diffraction pattern of a ring source. Okay, and then Airy disk and so on. So Airy patterns and so on. So here, if you have a ring source, what happens? If they are not distinguishable, then what happens? Okay, so this is, if they are not distinguishable, what happens? There's something very interesting happens. If you look at these 2 points, so you see this structure. So these are different parameters. Okay, for this parameter, this is this. This is actually the eigenfunction 16. Eigenfunction means n 16. But actually, I use 16 coherent states in a circle. The 16 coherent states combine, and all photons, they discuss each other. They say, okay, let us go to the level number 16. That is very comfortable. है ना, उसमें AC on है, चलो उधर, ठीक है? So all photons go to level number 16. So you get probability 1 in this case, and this is the eigenstate. So eigenstates are completely quantum, coherent states are classical. So you can see a classical quantum correspondence from here also, and also, you know, so this we call a dynamical condensation of photons, and for the diffraction limit, that kind of structure, you have a Bessel function at the middle. So we analytically proved this thing and reported that this structure is the same structure if you don't use coherent state, don't use quantum objects, but use circular source of light. And whatever structure you were supposed to observe in the middle, that is nothing but the one which you got from the quantum system. Okay, so there are very interesting, you know, aspects. You know, that is why things are not very intuitively very clear. Even fundamental things can give you a very remarkable discoveries. But now the third one is a ring waveguide and how you can get into the quantum information. But here you see the first one word with hyphen, matter wave. Matter wave. So de Broglie says what? Huh? लाइट का पार्टिकल आइंस्टाइन का नोबेल प्राइज मिल गया. अब de Broglie क्या बोला? So de Broglie बोला है. Yeah. So now you can think that, you know, Compton बोला है, ये बोला है, सबको नोबेल प्राइज कैसे मिलेगा? De Broglie, what new we have said? You know, de Broglie said very important things. Nature loves symmetry. So what happens that if light should be a particle, then matter should be a wave. Okay, and that is a kind of analogy, and then there is a intercorrelation. So a matter can be a wave. Now there is another state of matter, like, you know, solid, liquid, gas, right? Plasma, then matter wave. This is called matter wave. So what it does, that if you accumulate coherent photons, say I accumulate 10 coherent photons, what I get? A laser. Not 10, maybe more. A laser, coherent photons accumulate. If I accumulate coherent atoms, I get BC, Bose-Einstein condensate, or matter wave. Then those collection of atoms, they behave like wave. just like laser. Okay, so it's like an atom laser, atom behaving like laser. So different way of looking at optics. I'll give you several instances then how it is possible. You see here, fraction table you have seen. Now there is a ring on which I put, you can imagine laser, I'll put atom laser. Okay, this is the tunnel. So this is what you model, and say from top it will look like this. And then I would like to play this movie. Say I have a ring which is invisible here, you know, and then I have two what? Huh? Atom lasers. Yes, good. Atom lasers, two atom lasers. Why two? Because I want to see them symmetry. Let me. Right? Do you see several parts? Just like fractional revival you have seen, 2, 4, 8, 12 and so on, but much better than that, right? So it's a very clear, is going very fast, but you can see very clear snapshots. So it's not coming up above it, but anyway, you can see that different times, these are what? The atom lasers are getting bifurcated in different time, which is called fraction table. Now, what is this good for again? Is these two parts, like just like two covalent state. So they form Schrodinger cat. Four of them will be like a higher superpositions. So you can actually engineer quantum information science from this thing, which we have actually first time reported that this phenomenon exists even for matter. Okay, so I will not get it. So this is autocorrelation, what she was mentioning, this one. Yeah, so and that can give you a quantum sensing applications, physical superpositions, even in phase space also it can. And though these beautiful pictures, you know, it's called quantum carpet. Normal carpet जो होता है, it's called quantum carpet because it looks like carpet obtained from quantum theory. What is it? These bright spots are the flow of information, quantum information. So it's called quantum carpet. Okay. Now the fourth one. You see this one. Atomic beam splitter. Beam splitter सबको पता है. I think all of you have done experiments with beam splitter. है ना? You can also purchase beam splitter now. It is obtained in very cheap price. So how a beam splitter can be manufactured by atom. Okay, and that also will give you quantum sensing. Sensing, by now you know the meaning of it. So this is the way you see it is. You can see this. This is probably in actually in image kind of characteristics, explanations, holography. A lot of places, you know, you have to have optical setups. This is a very simple optical setup called optical waveguide. Okay, and you have mirror here, a beam splitter here, beam splitter here, beam splitter here. Now the wave is coming, is reflecting and also transmitting. And this is a reflecting surface, you reflect again and it goes on like this. But that is easy for optics. Laser, coherent laser डालो, ऐसा होगा, बिल्कुल होगा. Now, is it possible for matter wave? The answer is yes. Let me run this movie. So it strikes the first one. This splits into two. You see, is a beam splitter. One reflected, one transmitted. Then there are two. Then it goes on a lot of, you know, interesting things. So now it will be like, you know, mesh now, but they are not mesh. They are actually coming to a more important regime. What we reported is we can actually get into a very sophisticated interference patterns. This one and this one will tell you that, you know, how precisely I can measure several parameters, distance, momentum, and phase, and so on. Remarkably, the indirect measurements of temperature. Nobody has measured a picokelvin temperature. So the point is, can you differentiate 1 picokelvin and half picokelvin? Can you differentiate? In पेपर में है ऐसा 1 केल्विन पिको केल्विन लिखेंगे, हाफ पिको केल्विन लिखेंगे, ऐसा नहीं. Can you measure? There are two things. I say that this temperature is 1.2 picokelvin. Can you say whether it is 1.2? The answer is no. Okay, there is no classical means by which you can say that picokelvin precision of temperature is possible. Okay, so we have said that, you know, this we can probe into the level of picokelvin. by quantum superposition structure. Quantum machine learning सबको पता है आजकल, तो नहीं है ना? हैं? किसको नहीं पता है? सबको पता है. So machine learning is a kind of getting very famous with time, but by quantum computation, can we have algorithms in quantum machine learning? Because we have seen that quantum has a lot of disadvantages. What are disadvantages? One thing is it is probabilistic. पता ही नहीं है ये जो pointer इधर है या उधर है, right? So how can I hold it? That's the first problem, the probability. And then the problem is they are very fragile, very fragile. So they just decays like anything. Okay, so it's very difficult to measure. Now these are the two problems. But then why then people are so kind of eager to do quantum methods and technologies and so on? Because there are so many advantages that there's no other way but to get into these and overcome these problems. Okay, 2012 Nobel Prizes, I'll just get into after some time, that people are actually working on those things, how to minimize those problems. So quantum machine learning is, it relies on the quantum computation by coherent states, but here actually I have not written coherent states, but this is some initial state and final state. What is machine learning is that you learn machine, actually you teach lesson, the machine will be learned from you. You teach machine that okay, these are the things happening. Now you give some unknown thing, and the machine will have some experience from the previous data. Then machine will be able to identify. Okay, so first you train machine, then machine will give you the, just like a student, we train student and then you give a problem, chalo akela solve karo, hai na? So just like, so it is a machine does it, which is called machine learning. So this is a kind of algorithm which we have given with this is the circuits for it, the state preparation, measurements. Let us not get into it. Vivek is there. Vivek, if you ask Vivek, we will talk for 1 hour. No, Vivek is not here. Okay, so this is a test image. Test image means that the image which I have given to the machine. Image processing, it has been discussed quite a bit or no? Digital image processing. Okay, I think it will come at some point. So if you have an image and then is a image with full resolution, whatever is available, you give it to the machine and machine understands it. How? As a quantum image. Machine understands that, which machine? Quantum computer, the circuit, that is the machine. It understands as quantum image, and then you have image quality assessment. So होता है ना कि एक किसी का मोबाइल पे अच्छा फोटो आता है ना, तो क्वालिटी असेसमेंट. अभी देखो 5 फ्रेंड है ना, यू कंपेयर द फोटोज ऑफ अमंग ऑल दिस, ये तो होता है ना. तुम्हारा में जब फोटो खींचना है, अरे तुम आ जाओ फोटो खींचो तुम, है ना. So then you are doing image quality assessment, right? So if you have noises, you see that this picture is blurred, this is less blurred. So there are 1 layer, 2 layer, 3 layer, 4 layer, 5 layer, and so noises are superimposed just to check whether our algorithm, quantum algorithm, works or not. And what is the result? Result is this. The first one with this and this, it is 1. So exactly 1. That is obtained from not by looking, because machine understands only data. It cannot see the image, right? So this is 1, but this one is, you see the digit 0.978, right? 1 layer of noise, so it is deviating from 1, then it is deviating more, you see, right? Deviating more for all the images. So this is done with quantum computation. So machine learning with quantum computation. Okay, so this is the method which Vicky is working, that using, as I said, that 2 entangled photon pairs. इसके बाद एक एग्जांपल है, 2 स्लाइड खत्म, ठीक है. You should be optimistic ना सर, खत्म करेंगे. Okay, so crystal, a nonlinear crystal, you be light on it, and then it becomes a 2 being 1 and 2, and these 2 beams are entangled, automatically entangled. This is called spontaneous parametric down conversion. spontaneous. We do not have any control. We put light on the crystal, that crystal, nonlinear crystal, calcite, one of the examples. It will become by default entangled. And and what we do is we have this thing for non-diffracting wave. So this is a kind of airy beam, light beam. Okay, and if you put on the crystal normal light, you put on those crystals, they become entangled. So you don't have to go for atomic level. A beam can be entangled, quantum mechanically entangled. If you allow them to put on this, pass on this crystal, then you detect, and what is it? See, a coincidence count that measures the coherence between this and this beam and this beam. So this decides whether they are entangled or not, and we find it entangled. They preserve the shape and the output. So this is the way we go for the first entanglement for non-diffractive beams, which is airy beam. And this is the last one, which is entangled quantum superposition state using cavity QD. Cavity QD. Cavity, optical cavity. Have you heard about? So is a mirror, highly reflecting mirrors which are placed face to face. Okay. So if you put some light on it, say laser, the laser will not come out. That's why it is cavity. And inside all lasers, say this is a point laser. Inside this you have a cavity, and there's a gauge medium, and then it emits laser light. So this particular thing. There's one mirror, and there's another mirror. What is this? Greenish thing. This is a laser. Now, as I said, laser is nothing but. ये आंसर नहीं दोगे तो आगे नहीं बढ़ेंगे. हाँ? Coherent state. बच गया हूँ. So, इसमें coherent state है. This is a cavity, and you have a coherent state. So now the thing is, it is a quantum object now. So cavity quantum electrodynamics, because laser is an electromagnetic wave. So if you have some quantum information processing, then with this system is called cavity QED, and this is not very trivial. Harrows and Wineland, mainly Harrows. I met him twice. So Harrows has got Nobel Prize. This is Harrows standing here. This is the cavity here, and in 2012 for what? Just creating cavity QD experiment. That's no. They have minimized the decay. Two disadvantages I say, and created a series of experiments for creating Schrodinger cat state. Why? Because that is very much useful, as I have been telling since beginning. So they have created Schrodinger cat using this setup, which is somewhere here, and so this is a schematic. This is a cavity you can see. This is a Ramsey interferometer. Okay. Now I am sending one atom through this cavity. Okay. Remember, there is a coherent state inside it. Coherent state. Now I am sending atom. Okay. Let me send. Animation में भेजने में क्या जाता है ना? So भेज दिया. Now what will happen to this atom? So atom will, when this is passing through this cavity, then this laser and atom will interact. Okay, it will interact, atom will pass away, but then it will take the information of the cavity because they become entangled. So this quantities, this properties are further used. This is some, just to tell you decoherence. You see how they are decaying. Okay, domain. So how they are decaying, you see, this is what a compass state. North south is चार है ना ऐसे. Then in between you have interference structures. You see, due to decoherence means decay, environment effects, thermal effects, and so on. And because of that, this will decay very fast, and you cannot use anymore that state, because this individual thing is just like classical object. Unless you have quantum interferences, quantum entanglements, you are not going into the quantum domain. So they minimize all these things. Now this is our circuit. So this is around 35 pages calculation Batin has done. So this is one cavity, this is another cavity, Ramsey interferometer, three of them. So one atom goes, and this is also, this cavity is absent. Absent means I switch off. I do not, make it active. So second atom and third atom. So this is the quantum circuits for creating an entangled Schrodinger cat. Schrodinger cat, yaad hai? This is entangled between Schrodinger cat. It's not entangled between coherent state, entangled between Schrodinger cat. Now, Schrodinger cat itself is very much useful, right? Now, if I entangle them, in addition to superposition, I also give another feature of quantum mechanics, which is another very remarkable feature, which is entanglement. So, superposition and entanglement both are present. So, that will be anyway very useful for quantum sensing, right? So, these are the states, and they are entangled. You see, this is one cat state, very faint actually, and this is another cat, one horizontal, one vertical. Okay, so one cat is kept here, another cat is kept here, but they are entangled to get this kind of structure. Okay, and which is useful for quantum sensing. So each region can tell you the limit of quantum sensing, how precisely you can go with gravimeter, metrology, atomic clock, and so on. Decoherence. Well, it depends. It depends on the system to system. Say, if I take a coherent state, so that can be increased to minutes. Okay, but if I use some superposition, then it is fragile. Then they will they can go to milliseconds. Yes, so several milliseconds, not one. So most of the times, if you control decoherence a bit, you are able to measure quantum objects. Okay. So now you see one cat, one Schrodinger cat, and another Schrodinger cat, two cats, independent. I entangle them. So this is one of the states, psi phi. Remember Alice Bob, psi phi, and then if I make them entangle, what will happen? So I'm showing this animation this way, but they are not actually propagating to one another. This is the resultant state that what I wanted to show. It's a resultant state without moving to one another. You have one Schrodinger cat here, one Schrodinger cat here, that's all. Now I just entangle them. I don't bring them together. What will be their state? This is the combined state. Okay, with Chekhov structures and all. So what is the resultant state? Is this like a compass one, but I did not have this compass state in the beginning. So superposition and entanglement though both. So then things are further analyzed. So that is the thing. Now this is my team. These are all of their works, and so basically to conclude, I can give a lecture of 10 hours. That is the conclusion, only for elaborating whatever I have said. And in addition to that, we are also proposing quantum logic gates using matter wave, and several more applications on this. And so that's all. So this is my team, and thanks to all of you for listening to me for the end of the day. क्वेश्चन करने की एनर्जी है तो पूछो. हाँ, श्योर.